Good morning and good evening, everybody, wherever you are in the world. My name is Stefan Stoll, and I'd like to welcome you to the EasySpin Academy 2020. I'm a professor at the University of Washington in Seattle, and right now I'm streaming this from my basement in my home. Behind the scenes for this event is Stefan Pribitzer, who is managing all the online streams and infrastructure to make this happen. This is our first online EasySpin Academy. We have a large audience, and we hope that all the technology is going to work out. So what is EasySpin Academy about? It's a workshop. It's going to last 3 days, and we're going to cover the basics of EasySpin. We won't have time to go into any particular depth on any topic, but we'll have Q&A sessions every day where we can answer questions. We do assume some familiarity with MATLAB, which is the platform upon which EasySpin runs. And hopefully in the pre-workshop emails, you got a link to a MATLAB on-ramp course. We have 3 days to look at EasySpin. The day 1 covers the basics. On day 2, we'll mostly focus on least squares fitting, which is probably the most desired feature in EasySpin. And on day 3, we have time for more advanced topics, as well as some flexible sessions that we'll decide on day 2, depending on user need. A few organizational things first. All links are on the Academy website. So if you can't find the email with the links, just go to the Academy website. I'm going to show that quickly. easyspin.org/academy, and it will contain links to the schedule, to our YouTube live stream, to the Q&A website. Also, the demos can be downloaded. We'll have a virtual happy hour and so on. So the workshop is structured into a series of sessions. Each session lasts about 30 minutes, and then there's a 10-minute break after each session. So feel free to get up and get a coffee or a drink whenever you want. Each session consists of demos. So I will be presenting on a particular topic in each session that might last between 10 and 15 or 20 minutes. And for the remaining time of the sessions, I encourage you to look through the exercises which are given in the script, and maybe start doing them. Also just look through the script or browse the EasySpin documentation related to this topic. Everything is in script files, and we will provide exercise keys at the end of day 3, and we'll send them out via email. If you have questions, please use Slido. The link is provided on the Academy website, and the event code is ESA2020. It should be included in the link. Let me show you. If Slido fires up, you will need to enter your name and agree on some conditions here. Once Slido fires up, then the Q&A is happening, and we already have the first questions here. So that is Slido. So we don't know how many questions we'll get. So if there are any EasySpin experts in the audience, please feel free to answer questions from EasySpin novices. This way we can crowdsource the support a little bit. Questions that are not answered and we find important for the general audience, we'll answer in the Q&A session at the end. And if there are any topics that come up we think are worthwhile treating in more detail, we'll add them to the sessions on day 3. So at the end of every day, we'll have a virtual happy hour on a website called Gather, gather.town. The link is also provided in the email or on the Academy website. It's not accessible right now, it's password protected, but once the happy hour starts, you can just access it there and join us there for just some chats with everybody. So finally, people in my research lab, Lizzie Canary in my research lab has designed a t-shirt. And if you want to have an EasySpin Academy t-shirt, please go to Bonfire, EasySpin Academy 2020. I'm briefly going to show this as well. There we go. So you can choose several colors. It costs $15, and all the proceeds go to a non-profit organization. So we don't make any money from this. All right, I think these are all the main organizational things I wanted to get off our list here. And we'll start with the first session. The first session is a very introductory overview of EasySpin. And first, let's download the script files. So, organizing my screens here. So as described in the email, the EasySpin files come as a zip. The script files come as a zipped file, which you can download from the EasySpin Academy website. Once you downloaded this file, you need to unzip it and put it to any folder of your preference. I've already done that. And then if you start MATLAB, which I've already started, and in MATLAB, you will see on the top below the ribbon menu, you will see the current directory browser. And so if you open that there and then just navigate to the folder that you just unpacked from the zip file, I'm calling it ESA 2020, and then select folder. This will put the working directory of MATLAB right in there where the scripts are for the workshop. So what you're seeing here is the basic layout of MATLAB. We've got a command window, which serves as a calculator. And we can also define variables, for example, a equals 65. And these variables that are defined then show up in what's called the workspace browser, which is a separate panel. And you can see there's one entry for every variable that's defined. You can rearrange these panels as you like. For example, I can move this here. My general layout that I'm using for my work is I'm putting the workspace in the current folder on top and the command window on the bottom. And then I'm opening here on the top left, there's a new script button, not the new live script, but the new script button. And that opens an editor. And this editor I am docking here to the left. So the workflow I'm going to use is I'm going to type in the editor, which allows me to save whatever I type, and then run the code from the editor over in the command window. And I'll show you then how this is done later. Okay, I need to undock my file again. Voila. So what about EasySpin versions? EasySpin currently has two different versions, and when you go to the main website, you can download them both. There is a stable version, currently at 5.2.28. This has been around, 5.2 has been around for quite a while, and 28 means it's the 28th bug fix release. This is a stable version, it won't change much anymore, and lots of people are using that for their published research already. There is a development version, so we are working towards EasySpin 6.0 with a host of new features, and we're kind of halfway through the process. But we've already released the development version, so you can download it and use it. Currently, we are in the 26th iteration of the development. This version has more features, is more stable, and has fewer bugs than the stable version, and I recommend using this if you are okay with having the code change on you. Because as the development continues, some things might change. If you'd rather use something that is going to be stable, then go back to the stable version. But the development version has more features, and actually it's the one we're going to use in this workshop. So in order to follow along with the workshop, I also encourage you to download the development version here, and then we'll download the zip file. That zip file is about 7 megabytes. When you unpack it, just put those files in some folder of your choice. Then, in order to tell MATLAB about this folder, you need to go back to EasySpin, to the home ribbon here on top, and then find in the environment section the link called set path. If you click on that, you will get a dialog window where you can add the path to EasySpin. So you click add folder, and then you browse to where you downloaded it. And I downloaded it to the C drive here. I'm on a Windows machine. I'm going into that EasySpin folder, and within that EasySpin folder, there's 3 subfolders. It's important to be aware of them. The main one that contains the code is the EasySpin subfolder, and that's the one we'll have to add to the path. But there's a documentation subfolder that contains all the documentation. You don't have to go online to get the documentation. And the third folder contains a lot of examples. So if you drill in there, there's a ton of subdirectories with topically organized EasySpin examples. So you need to do now double click on EasySpin to make sure the EasySpin subfolder is activated, and then select folder to add it. And it will now add to the top of your MATLAB search path. This is the list of folders which MATLAB searches when you type a function name. It's trying to locate the function. In MATLAB, every file in this folder, in these folders, is considered a function. And when MATLAB finds a hit, it tries to run that file with that name. So save that search path, and close the window. And with this, EasySpin should be installed. To verify this, go to the command window and type EasySpin and press enter. And as you can see, it tells me that the release is exactly the one I wanted to install. It tells me where it's installed, and it does a few checks. And in case there's any name ambiguity or uncompiled parts of EasySpin, it will prompt you here and tell you that there is a problem. Okay, so now where can you find help about EasySpin? There's basically three sides, three different things. First of all, there's the documentation. The documentation, if you install 6.600, is locally in your EasySpin folder, documentation, and there try to find the index.html file. Index.html. And if you open this index.html file, I'm going to open this in Chrome here, it will directly take you to the main documentation site that is local. And you can see the documentation always tells you which version this documentation is for. You could also go online. So if you go online to easyspin.org, you will see that on the top right, there's a documentation button. But as of now, the documentation that's online is for the old EasySpin version, 5.2.28. So if you want to get the 6.0 documentation, you have to access it locally on your machine. Okay, then the second one we already talked about, which is the examples on the EasySpin in your EasySpin installation. And the third resource for you to learn about EasySpin is the forum. So if you're on the online, let's go back to the online website. On the top right, there is a link to EasySpin forum. And this EasySpin, so if you have questions and issues with some of your EasySpin code, please post questions there, and somebody will typically answer them within a few days. It's sometimes not very responsive, depending on how busy I am and how busy the other EasySpin experts are. Okay, so these are the resources how you can find help about EasySpin. Now we've set up MATLAB, we set up EasySpin. The first thing that you want to do as an EPR spectroscopist, of course, you want to get your data into MATLAB for analysis. So how to import data? There is an EasySpin function for that, and it's called EPR load. It supports a variety of file formats, and we're going to start out very simply. So we start with clear, which deletes all the variables that are defined. Right now, the workspace has two variables, but if I run clear, these will disappear. And I'm going to type CLC, which will clear the command window. So I'm just typing the script right now. I'm not running it yet. So then we're going to use EPR load to load a file. EPR load radical.dta. This is a mock spectrum, and these data files are within the EasySpin Academy script package that you downloaded. So what EPR load will do, it will take this file and import it. It will put the x-axis, magnetic field, into the variable B, and the spectrum into the variable SPC. And once we've got that, we can plot it. We just say plot B, SPC. Okay, enter. And now in order to run this code, what you need to do, you could either copy paste this over, all this code over to the command window, or much more simply, just be there and press Control Enter if you're on Windows, and I think Command Enter if you're on a Mac. So I'm pressing Control Enter now, And voila, it ran and it printed the spectrum. These figure windows you can also dock, and today I'm going to dock them in. Here's my typical layout. I'm having the figure window on the top right, command window on the bottom right, and the editor on the left. So this loaded a DTA DSC file, which is a Bruker spectrometer file format from the more modern spectrometers. But EasySpin also supports older files. For example, we can load an older file here, EPR load dpph.par or SPC. This is the old SPC par file that all the Bruker spectrometers had implemented. And now I can run this again with Control Enter. And then I'm plotting this as a simple DPPH spectrum. What you've seen here, I've added 2 percentage signs. So whenever you add 2 percentage signs, MATLAB subdivides your file into different sections. The current section where your cursor is in is typically highlighted. And if you press Control Enter, MATLAB will run just the code within your section you're in right now. So you can also get back from a third output argument. Let's call this parameters. The third argument returns parameters. So I'm going to run this now with Control Enter as usual. Now if I look at my workspace, I have 3 variables and the parameters is a MATLAB structure. So if I type this in a MATLAB in a command window with par, you'll see it contains a structure with lots of different fields which are exactly as specified in the parameter file. You can, in particular, you can say the microwave frequency, the receiver gain, the sweep width, the center field, and so on. So these are simple ways of importing data files. If you don't want to type, you don't know how your file name is called, you can do it interactively. Just say EPR load and run that with Control Enter. That will open up a file selection dialog, and you can now, for example, select another file. And if you open it, MATLAB should plot it. Where's my figure? There it is. Okay, so that's the interactive use of EPR load. If your data does not come from a Bruker spectrometer, but from some other acquisition software or other source, and you might have a text file or an Excel file, it's very easy to import from text files. Again, you're going to import B and SPC, and then use the function text read. You can give the name of the file, and I'm going to just use a simple text file that only has 2 columns of numbers in it. The first column being the magnetic field, and the second column being the spectral intensity. So we need to tell text read that there's 2 floating point numbers in each line, %F, and there is going to be no header lines. I'm going to briefly show this. Radical.txt. Let's open it up. And if you see here, there is 2 columns. So it's a pretty boring text file with no header information whatsoever. So some other text files might contain a header information, but in this case, no. So we say header lines 0. And then, of course, we can plot this again. And voila, here it is. In MATLAB, if you don't want any command or function to print to the command window, make sure to add a semicolon at the end of your line. This keeps your command window pretty tidy. You can always clear it out by typing CLC, which says clear command window. So there's other functions, of course, for Excel. If you might have Excel data, the function you need to use are you can either use read table or XLS read. But you can see more of this in the EasySpin documentation. There's a separate section, and if I'm going to go there, I'm going to my local EasySpin documentation. The very first section in the user guide is data import and export. Okay, data import works. Now you might do all sorts of EasySpin simulations and fittings and calculations. At the end of the day, you want to get your results out of MATLAB and of EasySpin into your platform where you're going to publish or present. So data export is also very simple. So let's again clear all the variables, clear the command line, and let's generate some data. Let's just pretend we have some data. It goes from the x-axis goes from 0 to 30 and has 201 points. Linspace is a very useful command. It generates a vector with numbers incrementing from the start value to the end value and with a given set number of points. Now I'm going to generate some, let's make a Gaussian function here, make a Gaussian peak centered at 15, and with some width. And then we're also going to add a little bit of noise. Let's say this much here, 0.2 with an amplitude of 0.2. And rand is a function, let's use rand n. Rand n is a function that generates normally distributed, which means Gaussian noise. And you can add that to your data. Okay, let's see how this looks like. This looks like a noisy Gaussian peak. In order to export that, you can either do the following. You could export that in a Bruker format, and for this use EPR save. EPR save my data x comma y. My data, that's the file name, and then x and y is the data I want to save. And you can also enter a data title, a description, basically. You can, if you run this, it will save a DSC and a DTA file. Let's see if it runs correctly. And if you go here, my data DSC and DTA has appeared. So EPR is very safe, is useful because then you can load whatever you've simulated with EasySpin back into a Bruker software, if you desire to do so. You might want to save the data in text format, and that's also fairly simple. What you do there, you have to combine the data into a single matrix in 2 columns. So convert X to a column format, convert Y to a column format, and then the square brackets put both columns together into an n by 2 array for the data. And we can look at that again in a workspace. You can see data is now is a variable that has 201 rows and 2 columns. Okay, and in order to save this, what you need to invoke is the command save, which is a MATLAB command, not an EasySpin command. You give the file name, myfile.txt. You tell it which data or which variable to save, and we call the variable data here, right? Data. So we need to give that variable name here. And importantly, we have to say it should save it as an ASCII file. Otherwise, it will save it as a MATLAB specific binary file. So if you run this, it will save, it should generate myfile.txt, right, which contains now a 2-column layout of your data. So this is the way how you get data out of MATLAB and EasySpin. So let's briefly talk about plotting and then how to get plots out of EasySpin. So here we have a plot. Let's stick with these data for now. If you want to make a new figure window, you just type figure, and I'm going to run this now. What you also can do, instead of running an entire section, if you just run a single line, what you need to do is just highlight that and press F9 on Windows and I think Shift F7 on Mac. And this, if you run this, it will open a new figure window, which you can easily dock in there. Okay, so let's take our data from previously. Plot XY, it's the simplest way to plot, right? But you also could want to plot in something in red. So you just add R at the end. Or you might want to plot this as dots, or as red dots or red circles. So you have lots of possibilities of customizing your plot. We can generate a second data set that has maybe a different scaling. And we can plot both of these at the same time. And the way to do that is plot XY, X, and Y2. And maybe we plot the first one as blue and the second with red as dots. And now you have 2 things plotted, or 2 traces plotted in the same graph. You can add an X label with X label. Let's call this frequency. Megahertz. Let's pretend this is some sort of nuclear spectrum like Endor or ECM. You can add a Y label. That's, we call it intensity. Intensities are always in arbitrary units. You can add a title called my title, say here, and you can turn the grid on, and and so on and so forth. So there's tons of ways of customizing your plot, and the best way is to read up on this on the MATLAB help. And MATLAB's documentation is actually outstanding. So you go to the very top right here, and you click this button, or you just press F1. That will fire up MATLAB's documentation. You go to MATLAB, and then there is an entire section on graphics. And that graphics contains plotting basics, how you do annotation, images, printing and saving, and so on. So printing and saving and getting your figure, the beautiful figure you generated out of MATLAB. So what you can do, you can generate a file. One way to do a file is called a print function. If you want to generate a pixel file, you could choose a PNG format. So then you use -d PNG. You can also specify the resolution you want to have, R resolution, let's say 600 dots per inch or DPI. And then the name, let's call it my figure. So that if you run this command, it will print the figure to a PNG file. You can also make a PDF file with print -d PDF and the figure name, the figure file name. Those are the ways of printing. Now, how large the image will appear in the PDF depends on what settings you have for the figure. And a figure here always has a size setting that's specific to the windows, and there's a separate size setting that's specific for printing. And in order to change that, you will have to look at the figure properties. And one way is to click on the figure. And if you click on the figure, a figure tab appears in the ribbon menu. You click there. And after a little bit of thinking, MATLAB will eventually bring up the menu bar, the property explorer, the property inspector. There it is. My computer is busy streaming, so things are a little slower than usual. In this property inspector, you can adjust the figure size that is used for printing. Position, you can adjust the positions here and adjust your figure. Okay. So finally, what you might also want to do is to export the figure and just copy paste it into a PowerPoint or Word file for your presentation. And the way to do that is you just go to the figure menu or the figure tab, to edit, and then to copy figure. And that will just put the figure into your clipboard, and then you can just insert it into another, into PowerPoint or Word. There is copy options, which allow you to set exactly what you want, whether it's a meta file or a bitmap, and what type of background it should use, and what size it should take out. So this brings me to the end of session 1 demonstrations, which showed you the basics of how to get data in and out of MATLAB and EasySpin and how to print figures. Please try now to unzip the script zip file we provided, maybe browse through these the script of session 1, and maybe do some of the exercises, and I'll see you back in about 11 minutes. Welcome back to session 2 of the EasySpin Academy 2020. In this session, we're going to look at the very basics that are needed to simulate EPR spectra, in particular the spin system and the interactions that we need to specify. Let's switch over to MATLAB and start a new file to explore. So the most important thing about a paramagnetic center or spin center is, of course, specifying what the electron spin is, how many unpaired electrons there are. In EasySpin, everything about the spin system is collected in a structure, and the most conventional name for it is cis. But you can name it any way you want. In order to give the electron spin, you just type cis dot uppercase S, and then you specify the electron spin quantum number. 1/2, for example, for a simple radical spin 1/2 particle. If you want to have a spin 5/2, just change this to 5/2. If you want to if you have a system of 2 coupled electron spins, for example, in a dinuclear metallic complex or a biradical, then you just make an array in square brackets with the 2 electron spin quantum numbers, 1/2 and 1/2, for example. You can put a comma in there, or you don't have to. Either way will work. So that is the basics of how you define an electron spin. Now the next thing that's important to specify is the G value or the G tensor of the radical or paramagnetic center. To do this, just type cis.g. And now you have several possibilities. You could, first of all, you could specify the full G tensor. And like every tensor, the G tensor comes with 3 principal values. And let's take an example here: 2.03, 2.04, and 2.2. This is a full, basically the full diagonal of a tensor. You can see the 3 numbers are different, and this symmetry is what we call a rhombic tensor. And the values here are typical for a copper complex. Sometimes the G tensor has higher symmetry. It might be axial, in which case the 2 first numbers are equal. Let's make an example here: 2.03, 2.03, 2.2. You don't have to write this out if it's axial. What you can do, you can just write 2.03, 2.2. In this case, EasySpin will know that the first principal value is both for the x and the y direction, and the third is for the z direction. Right? Just like for the rhombic tensor was the x value, the y value, and the z value. If you have multiple electrons, like for example up here with 2 electron spins, you can give a G tensor for each electron spin separately. So cis.g equals, and then in square brackets, you first give the G tensor for the first electron. Let's say 2.0, 2.1, 2.2. That is the first row of the matrix. Then a semicolon, which starts the second row. And then you enter the G tensor for the second electron spin. Let's say 1.93, 1.93, and 1.99. Just some fictitious example here. Okay, you could also, for a single spin, you can give the full G tensor, because a full G tensor actually is a 3x3 matrix. And when we specify just 3 numbers, what we are saying is that the matrix is diagonal, and we're only giving the diagonal values. So instead of just giving the principal values, you might also going to give the full G tensor. cis.g equals, and now you could write 2.0300 for the first row, 0, 2.040 for the second row, and 0, 0, 2.2 for the third row. And if you look at this briefly, you see I'm highlighting this with my cursor keys, and then I'm going to press F9 to evaluate this selection. You could also right click on this, and then there's the first item in the pop-up menu that says evaluate selection. Or I think on Mac it's Shift F9. So if you run this, you can see the answer in a command window, and it plots out the 3x3 G tensor matrix that we've defined. So Basically, this way of entering information about tensors applies not only to the G tensor, but also to all other tensors like hyperfine couplings and zero-field splittings, quadruple couplings. So next, actually, let's look up where we can find help about how to specify these tensors. If you go to the EasySpin documentation, the second item in the basics section is called the spin system. And if you look in there, we'll see after initial quick examples, you will see a quick overview of what everything can be defined from spins, G-values, hyperfine, nuclear quadrupoles, zero-field splittings. There's high-order operators. You can enter electron-electron spin couplings if you have a multi-spin system. EasySpin, as of 6.0, also supports nuclear shielding tensors, so kind of NMR sigma tensors. It also supports nucleus-nucleus spin-spin couplings, and you can also model paramagnetic centers that have orbital angular momenta and include spin-orbit interaction. There's also broadenings and some information on non-equilibrium populations. But let's click, for example, on zero-field splittings. On zero-field splittings, the help tells you that the field name that we need to use is D, and then there's a D frame option. Okay, so let's go back. Go back here and see what we can do. So first, zero-field splittings are only shift energy levels if the spin is larger than 1/2. So the smallest one is a triplet. So let's call this triplet.s, and it's going to be 1. You see, I'm not using cis here. I can use any name I want to identify the spin center I'm interested in. So we triplet.s equals 1. And now let's define zero-field splittings. Triplet.d, that is a zero-field splitting parameter. And let's put the number into 2870. This is always in units of megahertz. That is the default choice for all spin Hamiltonian all parameters in EasySpin. So 2870 megahertz is about 2.8 gigahertz. And this is the zero-field splitting for the nitrogen vacancy center in diamond, which is a carbon-centered defect radical in a diamond lattice. So this will generate, specifies a tensor that's axially symmetric, a zero-field splitting tensor. Sometimes you might have a rhombic D tensor. And then you would specify two numbers, let's say 1300 and 260. So again, everything's in megahertz. The first number specifies the D value, and the second number specifies the E value. So basically this is D and E. And again, it's in megahertz, right? As you can see, what I tend to do, and I think it's good practice, is to always add a comment after the end of a number you give that contains the unit for that particular quantity. Any comments in MATLAB start with a percentage sign, and so whatever you type after the percentage sign is ignored by MATLAB, and it's only for your own reference. You could also write this out in a different way. You could, for example, say 1300 times, and then 1, 0.2. Now what this means is first you define an array, and then you multiply each element of the array by 1300. Okay, this is basically the form of D times 1 and then E over D. And it's again in megahertz. And it's E over D is a very useful, it's useful to specify this way because you know, if the zero-field splitting is very large, the spectra at X band typically only depend on E over D and not on D directly. Okay, and finally, you could specify just the rhombic, the three principal values of the D tensor. For example, 400, 200, -600. And again, this is in megahertz. The first value is the principal value along the X direction. Second value is along the Y direction. And the third value is along the Z direction. In this case, the zero-field splitting tensor principal values add up to 0, and we say that the tensor is traceless, but that doesn't have to be the case. And again, like for the G tensor, you could also specify a full D tensor. So that's the basics about zero-field splitting. The next thing we should briefly look at are electron-electron couplings. So let's write out a spin system that has two spins 1/2. So cis.s equals 1/2, 1/2. Now, if you want to include an exchange coupling between these two electron spins, just add cis.j, uppercase J. And you can specify the coupling in strength again in megahertz. So for example, 5. Again, I annotate this with the megahertz comment. If there is a dipolar coupling, so a through space magnetic coupling between these two electron spins, you can add that by typing cis.dip for dipolar coupling. And let's say it's 3 megahertz. You might also want to calculate the full coupling tensor, the principal values. You could, for example, say cis.ee equals, and then some j value, which we define. Let's define a j value separately and a dipolar value separately. You see, these values are just variables. They're not part of the spin system yet. But you can define them and then use them to build your spin system parameters. So j times 1, 1, 1. This will generate an array of three numbers that are equal to j. And then we can add cis.dip, actually just dip times then 1, 1, minus 2. And this will construct the principal values of a dipolar coupling tensor. So this will be the full, this will be when you want to specify the full coupling tensor between two electron spins, which is a sum of the exchange coupling tensor and the dipolar coupling tensor. All right, what's the next thing? The next thing, we need to talk a little bit about nuclear spins. Right? A lot of chemical elements have magnetic isotopes, and you can look at that by typing isotopes. And so running this, or you can just type it directly in a command window. When you type this, it fires up a small tool that's part of EasySpin as well. It shows you a periodic table with all information about magnetic nuclei. For example, let's click on nitrogen. On nitrogen, you will see two entries in the table below. It's probably a little small for you to look at here in the live stream, but it will have an entry for nitrogen 14, which is a spin 1 nucleus, and an entry for nitrogen 15 with a spin 1/2 nucleus. It gives the nuclear G factors, which differ a little bit for these two isotopes. It will give you the resonance frequency of the given field, which you can modify here at the bottom. It also contains the nuclear quadrupole moment, if there is any, for nuclei that have a spin 1 or larger. And it gives the natural abundance. So for nitrogen, 99.6% is nitrogen 14, and 0.4% is nitrogen 15 in natural abundance. So that's a quick explorative table here. And now how to specify nuclei for a spin system for simulating an EPR spectrum. Well, you just add them to your spin system parameters. Cis dot, and now the field name after the dot is nukes. Uppercase N. Now, one important reminder here is that EasySpin is case sensitive, just like MATLAB. And so if you type lowercase n, like this here, EasySpin will not recognize this, and you might get a strange error message. So always make sure to check your spelling. In order to specify nucleus, all you need to do is make a character array or a string and type in the nuclear isotope. So quote 14N, quote closed. So this would specify just a 100% pure nitrogen 14 sample, which you might not have because typically you have a natural abundance mixture in your samples, right? Unless you do some isotope enrichment. To specify the natural abundance mixture, you type cis.nukes equals just n, and that will be the natural abundance. Now for nitrogen, that's probably a little bit exaggerated because we know that N15 only occurs with 0.4% abundance, and you probably will not observe it in the spectrum. because you don't have enough signal to noise. So in general, if you simulate a nitrogen spectrum, it is absolutely sufficient to just include N14. But that's not the case for other nuclei, for example, for copper. So cis.nukes equals copper will actually include the two isotopes. And I'm going here over to the command window and typing in isotopes. And then let's look at copper. Copper is here. Copper has two isotopes, 63 and 65, and they have 70% and 30% nuclear abundance. So if you have a copper spectrum, you always have to include both in a simulation. And the way to do this is just tell EasySpin you want a natural abundance mixture, which you get by just writing copper without any isotope prefix. If you have a pure isotope copper, for example, copper 63, you just add the 63 in front. Okay. If you need multiple nuclei, well, all you do is just concatenate them with commas. So let's say we have a radical that's centered on a nitrogen and has some couplings to some protons. We just make a comma separated list. So this would be a nitrogen, comma, a proton, comma, and another proton. And if you, let's say you have a system that's coupled to 2 chlorine molecules or 3, you would just write Cl, comma, Cl, comma, Cl. And chlorine is one other of these elements that has multiple isotopes with significant natural abundance. And now if you want to figure out how many different molecules that actually makes, you can use a command called isotopologues. Isotopologues, which basically this is an EasySpin function that generates for you all the combinations of all the isotopes that can exist in this molecule, and it calculates the associated natural abundances. So let's see what we get for just Cl for 2 chlorines. For 2 chlorines, if you run this, I'm selecting it and I'm pressing F9. We can see that we get a table, and it tells us there's a 57% abundance of a molecule with 37 chlorines, and there's an 18% abundance of a molecule with a 35 chlorine, a 37 chlorine, and so on and so forth. So there's a total of 4 isotopologues. Okay. So when you deal with these type of mixtures, natural abundance mixtures, EasySpin is automatically taking care of those. So as soon as you write Cl or copper or N, when you simulate an EPR spectrum, EasySpin will internally simulate all the different isotope spectra and add them together. So you don't have to worry about this at all. You can specify also non-natural isotope mixtures. Let's say you had some money, you bought some sulfur 33 or oxygen 17, and maybe it's only 80% enriched, right? Then you have to take care of 80% O17 and 20% O16 in your sample, and it will generate, at least 2 EPR spectra that always come together. You can do that as well. The syntax is a little more extended, and you can find that easily in the documentation. All right, so now we've got nuclear spins specified. Nuclear spins couple to electron spins via hyperfine coupling interaction. And to specify a hyperfine coupling, it's very simple. You use a field called cis.a, where the uppercase A stands for the hyperfine coupling tensor. And same for the G tensor, you can specify either just a single value if you want to have it isotropic, right? You can specify 2 values, say 2500 if it's axial. And again, I'm adding the unit annotations. It's always in megahertz. Or you can specify the 3 principal values for any tensor. And here would be, for example, a rhombic tensor. 20, 30, and 100 megahertz. So it's also possible to specify the full A tensor, of course. And it's very analogous to the G tensor before. If you have multiple nuclei, you basically specify 1 hyperfine coupling tensor per row. So let's say we have a 63 copper and a 14N in our spin system. Then we have two hyperfine couplings. Let's say the copper is 20, 30, 400 megahertz. Then semicolon to just start the second row. And let's say -8, -5, and 20 megahertz. The first three numbers are for copper, and the second three numbers are for nitrogen. This is how this works. So we've had G tensors, D tensors, and hyperfine coupling tensors so far. If you're doing nuclear hyperfine spectroscopy, you're running ENDOR or ECM spectra, you might also need the nuclear quadrupole coupling. So nuclei that have a spin larger than 1/2, so they spin 1, 3/2, and so on, they are non-spherical and they have they interact with their local electric field distribution, and that adds a term to the spin Hamiltonian that needs to be included in the simulation. And the field for the nuclear quadrupole coupling is called Q, uppercase Q. So sys.Q equals, and you could, for example, enter 0.7. That will be for E square QQ over H equals 0.7 megahertz. This E square QQ over H is the standard parameter that is used to specify nuclear quadrupole couplings. Now, if you want to have two nuclei, what you need to do is just again specify two rows with two different values. So this will be for two nuclei in megahertz as always. By convention, the second parameter for the quadrupole coupling besides E square QQ is eta, which is the rhombicity. And if you have that, you can specify that as well. So for example, 0.2 and 0.1, actually let's make this a little larger here. This here, if you give two numbers for one nucleus, then the first number would be the E square QQ over H, and the second number is the eta. And now the E square Q over H is in megahertz, but eta is just a number. Eta has no units. So this input is a little inconsistent with all the other tensors, but it's consistent with the dominant convention in the field, which we thought was more important than the consistency with the other tensors. But of course, you can also specify a full Q tensor. For example, you could say sys.Q equals negative 1.5, negative 0.8, and plus 2.3. This is in megahertz, and this will be the full tensor. Okay. So that kind of summarizes the most important fields that you need to specify in order to get a simulation started about your spin system. I encourage you now to look through the script of this session. Maybe start looking at one of the exercises that are interspersed with what I've shown you, and also look at the documentation for the spin system. And this concludes the second session of the EasySpin Academy, and I'll see you back in a little bit for session number 3, which starts in about 16 minutes. See you. Welcome back. This is the session 3 from EasySpin Academy 2020. In this session, we'll now do our first EPR spectral simulation. EasySpin's spectral simulations are grouped by different regimes. And in order to see this, let's go look at the documentation. If you go to your documentation, you will see that there's a large section on spectral simulations, and most of them are for continuous wave EPR. There's some general experimental parameter considerations, and then there's a specific function for the isotropic and the fast motion regimes. That function is called garlic. There is a function for slow motion regime, so when a radical is in solution but doesn't tumble fast enough to average out only anisotropies, and that function is called chili. Then there is a method for trajectory-based simulation dynamics, and then a very important function called pepper that allows you to simulate solid-state EPR spectra. So depending on the state of your sample, you have to use a different function. Pepper for solids, garlic for liquids, and chili for the in-between regime where your center is just moving very slowly. In this session, we talk about garlic. Garlic is the function for the isotropic limit. So if the molecule tumbles really fast, so everything averages out and you get just a series of sharp lines. Okay, let's start out. Clear, I always do clear to clear out the workspace of any leftover variables that might interfere with what I'm doing. Let's define a spin system for a simple radical. Sys.g equals to, let's say 2. And we'll also define, if you want to simulate an EPR spectrum, we also have to define a broadening, a line width. Now there's different ways of specifying how to broaden lines. And the first and simplest one is just a convolutional broadening. That will just mean that EasySpin will simulate a stick spectrum of where your resonance line is and just broaden that stick spectrum with a specific line shape. And to do this, use sys.lwpp. Now LWPP stands for line width, peak to peak. And you can give 1 or 2 numbers. If you give 1 number, it's the Gaussian. It's a Gaussian broadening. If you give 2 numbers, the second number will be the Lorentzian broadening. Okay, so that's all we need for a simple radical signal. We need the G value and the broadening. That is all for the sample. Now, the experiment. The experiment is a separate MATLAB structure, and the conventional name for it is exp. But you can name it any way you want. And the only thing that's needed for a basic simulation is the microwave frequency. You need to tell EasySpin whether you're at X band or Q band or W band. And to do that, write MW fric equals, and then let's say 9.5. This is in gigahertz. So all microwave frequencies in EasySpin are in gigahertz. Again, I want to remind you to be careful about your spelling. There's an uppercase F, lowercase MW. If you don't spell it this way, EasySpin will not recognize the input. So finally, what we need to do, we need to call garlic, which is the simulation function, and supply it with information about the sample, system, and experiment. Let's put a semicolon at the end. Now, if you don't ask it for any output, and if you run this now by pressing Control Enter on Windows or Command Enter on the Mac, you should get a simulation and a plot. And as you can see, we get a label plot with the resonance line with a certain width, and if you look at the width, it is going to be exactly 0.3 Gauss, 0.3 millitesla peak to peak. So from the maximum here is at about, what does it say? I have to zoom out. Anyway, so it's 0.3 peak to peak. Magnetic field units in EasySpin are millitesla. So to remind you that 1 millitesla equals 10 Gauss. So it's a very easy conversion if you use to Gauss to get to millitesla. And as you've seen here, garlic was able to find the field range automatically. It shows a field range that nicely accommodates the full spectrum plus a little baseline left and right. Garlic is generally able to do that, but other EasySpin functions might not be able to figure out in advance what the appropriate field range is. In the general case, you actually have to simulate the spectrum in order to know how it looks like. But for simple spin system, there are some heuristics EasySpin applies to determine a field range. It might not be quite on sometimes. So in those cases, I recommend just specifying your own field range. And we'll get to that. So how are we going to specify a field range? Well, what you can do is you add another field to the experiment structure, exp.range. That specifies the field range. You have to provide two numbers, the starting field, let's say 315 millitesla, and the end field, 355. So the lower and upper limit. And then these are in milliteslas. Okay, if you run this now, we'll get the appropriate field range, and the line is still at the same resonance field as it was before. It looks narrower because now the field range is much larger. There is a second possibility to define the experiment range. I'm just going to comment this out. And the second possibility is to use a center and a sweep, a center field and a sweep range. EasySpin takes this with the field center sweep, and you have to give two numbers. The first one is the center field. Let's say, what is it here? We can zoom in. So if you mouse over your figure on the top right, you will have a little menu that pops up. There's a zoom in button, and if you zoom in, we can see the zero crossing of the line is about 339.3. So we can center our field at 339.3 millitesla, and maybe just do a 5 millitesla sweep width. Okay, and now you see we're nicely centered. If you happen to specify both a range and a center sweep, then EasySpin will tell you, if you run this now with Control Enter, it will actually tell you that it's using exp centers field, and it's ignoring the range, exp range. When you measure an EPR spectrum, you also have to specify, or typically you know the number of points you acquired. Either you specified it or the software chose it for you automatically. EasySpin typically uses 1,024 points by default, but you can change that default depending to what you need. So for example, we can now add, let's remove the center sweep again and say exp endpoints equals 70. Endpoints is the field that you need to give. And then semicolon to suppress output in the command window. You can run the whole thing by pressing Control Enter. And now we're getting an error. Now it's telling us that the Gaussian line width is smaller than the increment, and it cannot perform the convolution. It means that your line width is so narrow that the whole line falls between two field increments. So what you need to do in this case, you need to increase your number of points. Let's go to 500. And voila, that worked fine. And so that is an important point that people sometimes run into, that their field resolution is insufficient to accommodate the very narrow lines they're trying to simulate. Okay, that is about the field range and the number of points. Let's briefly look a little more about the convolution, at this convolutional broadening. First, I'm going to narrow the field range a little bit more so we can actually see what's going on. I'm going to zoom in by narrowing the field range. Voila. So now we've got a nice zoom in onto the spectrum. Now let's modify the line width broadening. So this is the Gaussian broadening, as already said, of 0.3 millitesla, but we can make it a Lorentzian broadening by making it an array of two numbers. The first number being the Gaussian broadening, peak to peak, and the second number being the Lorentzian broadening. So in a way, Gaussian peak to peak and Lorentzian peak to peak. And of course, I'm sorry, what did I do here? This is as always in millitesla. If you run this whole script now I'm going to run all of this here, but just pressing Control Enter. We'll see now that the line shape changed. We get a Lorentzian line, which has much more extended wings that go out pretty far. You can also combine the two, and actually let's make plots. Before we do that, let's just generate a plot. We're going to ask Garlic to not plot the spectrum, but actually return it to us in two variables, B and spec1. This will instruct Garlic just to skip the plotting and just store the simulation results in these two variables. And let's actually make a nice comparison here. Let's put the experiment on top just for right order. Let's first simulate a Lorentzian spectrum. Let's call it spec L because it's for Lorentzian. And then copy paste this and just change it to a Gaussian and call this spec G and plot the two at the same time. Plot B comma spec L comma B comma spec G. This way we're plotting two things at the same time. And voila, here you can see it. In the plot you can see that in blue that's the Lorentzian line shape, and in the red there's a Gaussian line shape. We can add a legend to this figure. Legend, so the first one was Lorentzian broadening, the second one was a Gaussian broadening. The command is legend. And if I run the whole section again with Control Enter, it should be adding the legend, which now shows up in the top right corner. But you can move that around and you can configure it, have no frame and so on. But one thing of note here is that the Gaussian line looks more intense than the Lorentzian line. And so how does EasySpin actually determine the intensity of a spectrum? Well, in EasySpin, every simulation of a spectrum assumes the same number of spins. Right? Now, the Gaussian line is much narrower than the Lorentzian line. Right? The red curve does not extend as far out. So if you would do the double integral, which is what the procedure you would use to determine the number of spins, these two spectra actually would give the same number. But because the red spectrum is narrower, it will be taller. So that's an important thing to keep in mind. EasySpin is quantitative in terms of the number of spins. So if you have two very different spectra from two different spin systems, they're always referring to the same number of spins. An important caveat though is that EasySpin only simulates unsaturated spectra. Right? So if your experiment is such that your microwave power was too high and you saturated part or all of your spectrum, then you can't quantitate the spin anymore, and also EasySpin can't properly extract the number of spins from that. Okay, now what if you have a mixture of a Lorentzian and a Gaussian? We can add that as well. We're gonna copy this two lines, put them here, and now just split the 0.3 up between a Gaussian and a Lorentzian with 0.15, 0.15 each. Let's call this spec of the mixture and add this to the plot, B comma spec M. If you run this, we see that it's kind of in between. The intensity is reduced. We have a little bit of the outer wings in the yellow spectrum, but we also have the fairly sharp peaked shape at the center of the line. So that's how you specify Lorentzian broadening. If you want to rescale and want to plot them on the same scale and scale them to the maximum, all you need to do is just divide each spectrum by its maximum. So spec L divided by the maximum of spec L. So that will give a rescaled spectrum. Spec G divided by the maximum of spec G. And spec M divided by the maximum of spec M. And then Control Enter. And voila, now you can clearly see that the shapes are indeed different. If you're trying to follow along by typing and you can't catch up, don't worry. We'll provide all these scripts, including solution to the exercises afterwards. So for now, probably it's just easier to watch along and take notes, take side notes for yourself. Okay. An important thing to mention is when to use sys.lw versus another line with broadening parameters called sys.lw without the pp. So the first one is the peak-to-peak broadening, and that is very useful if you're running or simulating a continuous wave EPR spectrum, where you really the visual quantity is really the peak-to-peak width. So this is good for CW EPR. If you are simulating an absorption spectrum, let's say that's something you measured in a a transient EPR or pulse EPR experiment, then it's better to use LW, because that uses the full width to half maximum for the absorption spectrum. And that's something that's easier to read off in an absorption spectrum. So you have two different ways of specifying convolutional line width broadening, and you can't use both at the same time. I think EasySpin will either tell you it prefers one over the other, or he will just give an error and says, just give me one of the two. So that is convolutional broadening. Next, let's add some hyperfine couplings and some nuclei. So we're going to clear out the figure with CLF. We're going to clear the workspace. So right now, let's look over to the workspace. We've got the series of variables defined. If you start a new kind of modeling or a new little job, always clear your workspace. That helps you avoid any interference from previously defined variables. Okay, organic radical with G equals 2. Let's now add one proton. Nukes, 1H. Let's add a hyperfine coupling of 100 megahertz and add a convolutional peak-to-peak Gaussian line width broadening of 0.1 millitesla. Let's specify the microwave frequency for the experiment. Let's say 9.6 gigahertz, and let EasySpin choose by itself what the field range is. Okay, so now if you run this, we're getting a spectrum with two lines, split by about the equivalent of 100 megahertz in millitesla. Okay, so that's as simple as that. And you can just keep adding protons and also adding hyperfine couplings. I'm just adding one more here. And then you get more and more of these hyperfine splittings. Now, if you don't specify a line width, so let's say the line width to 0, what will happen if I press Control Enter? Garlic simulates just a stick spectrum. Now you can see that it's an absorption spectrum, so the intensity is positive, and you just get sticks at the resonance positions. And this kind of shows you what Garlic does, or EasySpin in general. It first simulates a stick spectrum, and then convolutes each stick with the desired line shape to give you the final broadening. That is the simplest broadening model. There's other broadening models we're going to talk about later when we get to solid state EPR. Okay. Next, what happens if you have equivalent nuclei? I guess let's go back to one nucleus here. Actually, let's copy this section. You can always copy a section down here. Let's go back to one nucleus and say we've got one with let's say 30 megahertz coupling. Especially in organic radical, let's add a little line width here, 0.5 millitesla. Voila, it's too much. 0.2. Voila. In organic radicals, often you have the electron spin is coupled to a series of protons, and if the symmetry of the radical is high, couplings to some of these protons might be identical. Right? And for liquid state EPR, you can tell EasySpin about that by saying sys.n and then giving the number of protons or nuclei that have that specific hyperfine coupling. So for example, if there are two hyperfines, two protons with a 30 megahertz hyperfine coupling, you just say n equals 2. Okay, and if you run this, voila, you get a spectrum with the expected 1 to 2 to 1 ratio. If you have 5 of them, you get this way, and if you have 50 of them, you get the spectrum looks like this, and if you have 100 of them, you get an error. And the errors, always, if you get an error, it's going to be red. I'm going to clear this out again so you can see it. An error always prints in red in a command window. And there's always a lot of debugging information, but the second line typically is the error message. So what EasySpin actually found wrong. And here it says that the Gaussian line width is smaller than the increment and cannot perform the convolution. So again, we have the situation where the lines are so narrow or the field range is so wide that the resolution is not sufficient to catch each line. what we need to do in this case, as before, is increase the number of points, endpoints. X.endpoints equals, and I'm going to put in like 10,000 points. See if, or maybe 50,000. That should definitely be sufficient. So if you run this with Control Enter, voila, we get a spectrum now. This is a spectrum of 100 protons. And you know, if you go again, if you zoom in to the tails, you'll see there's a lot of peaks that you will probably have a hard time measuring in an instrument because you require such high signal to noise ratio. Okay, so this is how you specify multiple equivalent nuclei. Let's increase the hyperfine coupling actually, let's say to 100 megahertz. Notice the spectrum here, it looks fairly symmetric, right? Now if you go to 100 megahertz, what you see is we're slowly getting into a regime where things are not entirely symmetric anymore. And the reason for that is our second order effects, which EasySpin automatically takes into account. So you don't have to worry about that, it's all taken care of under the hood. If your hyperfine coupling is large, second order effects are included. Okay, now next topic that we briefly need to look at are harmonics. As you know, typically CW EPR just measures the first harmonic, but EasySpin allows you to basically specify which harmonic you want to simulate. Let's just clear everything out and then clear the figure. Start with a spin that's a 31 phosphorus, let's say, with a coupling of 40 megahertz as usual, and some line width broadening of, let's say, 0.1 millitesla. Okay, I'm not specifying sys.s. I could, but if you don't give sys.s, it's automatically assumed to be spin 1/2. Okay, let's now give the microwave frequency, let's see 9.3, and then an exp harmonic, specify the harmonic. We can start with 0 and simulate that, asking Garlic to return us the simulation. And then we can copy and paste this and just simulate the first and the second harmonic. And we could plot this all in the same plot, or we can make 3 different plots. And let's do that. The command for that is called subplot. This is extremely useful. It takes 3 inputs. The first 2 lay out a grid of plots in your figure. And if I type 3, 1, it means we have like 3 rows and 1 column of plots. And then the third number tells us it's the index of which plot you want to plot in next. So 1 will indicate you want to put it in the first plot. What we're going to plot there is going to be in spec 0. Okay. And let's copy this twice and just increment the plot index and the spectral index that we simulated. We're going to call this spec 1 and spec 2. So the code is a little repetitive, but it's kind of short enough that it's not worthwhile writing a for loop or something. Okay, so if you run this, we get 3 spectra plotted on top of each other. You can say 3 subplots, 1, 2, and 3. And the top one shows the absorption spectrum. The second one is the first harmonic. And the third spectrum here is the second harmonic. So all you need to do is set exp.harmonic. And it might be, this is often very useful because if you know, I personally prefer to look at absorption spectra. They're much more intuitive than derivative spectra that are typically measured. And in EasySpin, it's easy. You just set the harmonic to 0, and when you then later want to do fitting, you set the harmonic to 1. So that brings us to field modulation, right? So the fact that we're seeing this first harmonic is a result of applying field modulation during the measurement in the spectrometer and then doing lock-in detection at the first harmonic. Let's do the field modulation. EasySpin lets you specify the field modulation automatically. So I'm going to copy everything down for our sample and the microwave frequency. And now I'm going to just simulate the spectrum just for ourselves. Voila, 2 lines. They look all good. Now let's add a modulation amplitude of, let's say, 0.1 millitesla. Again, this is millitesla. This is gigahertz. This will apply an actual field modulation, and that then really corresponds to what you do experimentally. Before, in the previous demonstration up here, EasySpin just took the derivatives in order to kind of emulate the field modulation. All right, if you run this, it doesn't look much different. Maybe some of you saw a tiny little broadening, but if you now increase the field modulation a lot, let's say to 0.5 millitesla or 5 Gauss, you see that we're starting to distort the line shape. And this is called overmodulation. If your modulation amplitude is larger than your line width. And EasySpin can take care of that. Okay? So that's actually an important point. There is sometimes situations where you want to overmodulate in your experiment. For example, if you're really struggling for signal, overmodulation gives you a stronger signal, and this would allow you to measure weaker concentrations of your paramagnetic center. The good thing is now in EasySpin, you can just include this overmodulation in your simulation. So even though the spectrum is theoretically distorted, you can still perfectly simulate it. It's reproducible. So keep that in mind. So that is field modulation. Maybe the last thing we'll need to talk about in this session, how we're doing time-wise, is options, simulation options. As you've seen, Garlic, like any other simulation function in EasySpin, takes two inputs. The first input is the information about the sample, and the second input is the information about the experiment. Now, there can be a third input. And I'm going to just copy-paste some settings from which I've prepared here, so I don't have to type it out. Here is a spin system, the G value of 2, 3 protons, each of them coupled with 78 megahertz. This is a mathematical, actually. X-band, 9.5 gigahertz with a lot of points, and we're going to look at the absorption spectrum. Let's run it. Voila. And what you can see is we have a stick spectrum. We should actually get, why do we not get the modulation here? Because maybe it's too small. It's a harmonic, no, it's good. It's the absorption spectrum. So as you can see, we have an absorption spectrum with very narrow lines. Okay, now Garlic, like any other EasySpin simulation function, can take a third input argument, which are simulation options, traditionally called just opt. And one thing you can do is you can specify the simulation theory level in a field called method. And the first thing, the most important method, of course, is the exact method, and that's the one that's being used generally, right? And that's the default method. But you can also use perturbation theory. For example, perturb1 would be the first order perturbation theory. And then you can see the spectrum changes a tiny little bit. And if you go to second order perturbation theory, we'll see that now we'll get the second order splitting in the central lines here. Right? Let's go back to first order perturbation theory, perturb1. You can see we have 3 protons, and so you expect an intensity ratio of 1 to 3 to 3 to 1, as we see. That is kind of the simple splitting pattern. But as soon as you go to second order perturbation theory, you see that the 2 central peaks, they split into 2 separate peaks. Experimentally, these might not be easily resolvable for every system, but for mathematical, they are definitely resolvable. So we can also plot the 2 things in parallel. So we can just call B spec 1, this, and then we just copy paste this, and maybe just use the exact method and compare it to perturb1. And the exact method, let's call it spec 0. And just say plot B comma spec 0, B comma spec 1. Add a quick legend exact, and perturb 1. All right, and there you can now see the comparison between the blue and the red spectrum. In particular, if you zoom in, you see that that's higher order splitting that comes in. So the red is an approximation, and the blue is the actual correct simulations, which EasySpin does by default. So there's a lot of options for these simulation functions. And the best way is just to look at them and find out about them looking at the documentation. And one section of the documentation that's really important is the function reference here. It contains a list of all EasySpin functions sorted by category, and also a separate list of all EasySpin functions in alphabetical order. Right? So if you want to find a specific function, or you want to figure out whether EasySpin has a function for a certain task, these two lists are the ones to look at. The most important core functions are listed here. And the first one, garlic, is what we looked at. If you click on that, you get the reference page for garlic, and it has the simulation options method, which we've looked at, and exact in a perturbation theory is implemented up to 5th order. And there's various other settings that can be adjusted. All right, this concludes session 3 about liquid state CW EPR. Please have a look at the script, glance at the exercises, maybe start them, or just take a break. If you have questions, head over to Slido and people will answer them. And I heard from, and I saw that lots of you are already contributing to answering the questions. Thank you so much. It's a great community effort. And see you in the next session, which starts in 9 minutes. Bye. Welcome back. This is session 4 of the EasySpin Academy 2020. In this session, we're going to look at solid-state EPR. So for solid-state EPR, the dedicated function is called PEPR, which is an abbreviation for powder EPR. PEPR allows you to simulate spectra of any solid, of crystals, of powders, and of frozen solutions. Let's start with a very simple example. Again, let's clear everything out here. Define a spin system with now 3 G values. Let's say the Gx is 2.10, the Gy is 2.10, and the Gz is 2.56. This will be typical for a nickel 1 species. Let's add some broadening, convolutional Gaussian broadening with LWPP. Let's say 1 millitesla for simplicity. This is exactly the same as we did for the liquid state simulations. The sample definition, all the sample definitions work exactly the same. For the experiment, the minimum required is the microwave frequency. Let's stay again at X band, 9.5 gigahertz. All we need to do now for the solid state spectrum is to call PEPR for the system and the experiment. And if we press enter, control enter, we'll receive the simulation. As you can see, there's the powder spectrum with a sharp positive feature for the GZ value, 2.56, and then the up and down feature for the GX and the GY direction. So PEPR works exactly the same way as garlic, except it uses a different theory and it assumes that you want to simulate the solid state spectrum. If you don't tell it to simulate a crystal, it will always simulate the powder or a frozen solution. So meaning that it assumes all the paramagnetic molecules are randomly and uniformly distributed in orientation within the sample. You can also plot the absorption spectrum by saying x dot harmonic equals 0. So this would be absorption spectrum. Again, if you run this section by pressing Control Enter on Windows or Command Enter on Mac, we get the absorption spectrum. Now you can see actually the absorption goes from about 265 millitesla all the way to above 320 millitesla. If you had a look at the first derivative, right, you would think there is no absorption here in the middle, but in fact there is. The absorption just has a very slow slope, a very shallow slope, meaning that its first derivative is essentially very close to 0. Okay, this is the absorption spectrum, and we can of course ask PEPR to give us back the field and the spectrum and just plot it ourselves, or if you want to export it or save it in a file. And voila, it is. It's not as decorated, the plot, as PEPR does it, but that's how it works. So the two major things that in which simulations in solid state differ from liquid state. First of all, you always need to include the full G tensors. In a liquid state simulation, you could supply this type of full G tensor, but garlic would just then take the average and use the average G value for the simulation. But for solids, you always have to specify the full tensors because the molecules don't move, and so you will have anisotropy. The spectrum will depend on how the molecule is oriented in the spectrometer. And since you have all orientations, we're going to sum over all these different spectra to give the full, what we call the powder spectrum. So the second difference to the liquid state is that now we need to sometimes take into account different broadening mechanisms. We actually have to think about the physics behind broadening. So in a frozen solution of let's say a small complex, in our case, let's say this nickel complex, when you freeze them, and the nickel is coordinated by some external, some ligands, the freezing will result in strains and different solvent crystallites that kind of push and pull on the ligands. And as a consequence, they will change the local geometry a little bit. And these small random changes to the local geometry are going to be different from one nickel complex molecule to the other in your sample. And these small structural changes, of course, have electronic effects, and they will slightly perturb your G tensor. So from molecule to molecule, the G tensor will have slightly different values. Or, as we say, the G tensor has a strain, or it's distributed. And EasySpin can include this type of broadening very easily. And if you have multiple, the G tensor is not a uniquely defined number, but a distribution, it will broaden your spectrum. Right? Let's do that. So again, we remove the convolutional broadening, LWPP, which is just, broadens the line in the spectrum without thinking about the physics behind it. And we're going to add now a so-called G-strain. And G-strain takes three numbers, one for each of the G values, basically gives the width of the distribution of that particular G value. Let's put in 0.002. Actually, no, I'm going to use some different G values here. 2.00, 2.19, and 2.37. Okay. And then 2.03, and let's say, what did I prepare here? 0.1. So these are the mean G values of the distribution. So on average, the average GX value is 2.00, and the distribution of GX values among those molecules in your sample is 0.02. This is the full width half maximum of the distribution. You can see the GX value is pretty narrowly distributed, GY is a little broader, and the GZ in this particular simulation we're going to assume to be the broadest. If you run this again with Control-Enter, you will get a broad absorption spectrum. You can see a kind of a axial, a rhombic spectrum with three features here, like the rising feature, a peak, and a dropping feature. This is the first harmonic, the absorption. Let's go to the first harmonic. Okay, see the field range. EasySpin wasn't quite able to figure out the field range to come back to baseline, so we're going to add the baseline ourselves with giving the field range x.range equals, maybe we should go down to about maybe 270 and up to 350. So from 270 to 350 millitesla. And let's run this again with Control-Enter or Command-Enter. Voila, now we've got baseline on both sides. Now what you can see is that the low field feature is much broader than the high field feature. The low field is from the highest G value, which is 2.37, and that's the one we broadened the most. And the high field feature is from the lowest G value, 2.00, and that one had the smallest broadening, right? So as you can see, it's physically possible that different parts of the spectrum have different broadenings, and that's a result of this orientation-dependent sensitivity of the G values to structural distortions. So these are called strain broadenings, and they're available not just for the G tensor, but also for the hyperfine tensors and the zero-field splitting tensors, and also, I think, for the quadrupole tensors, but I'm not entirely sure. And they allow you to model this kind of structural heterogeneous distribution of structures. There is one big assumption behind these G-strain strain broadening models in EasySpin, and that is that these distributions are narrow relative to the mean. So for example, 0.02 is small relative to 2.00, right? It's like 1%. As soon as the strain distribution width hits maybe 5% or 10% of the actual mean value, then the approximation within EasySpin does not quite work as well anymore. And you're better off writing your own for loop, basically simulating spectra with slightly different G values and adding them all up. And that will give you the same result. And for larger distributions, that will give you a correct result. Whereas EasySpin assumes the distributions are fairly small. Next, an important thing for solid states are tensor frames. Okay, so let's take a simple example. I'm going to just pick something I've prepared. It is a rhombic G tensor, spin 1/2, one coupled to one proton, and the hyperfine coupling is rhombic, so three different principal values and large, 60, 120, 200 megahertz. And we just use convolutional broadening. Let's go back to that simple phenomenological broadening. Let's run this at X band with a certain range. And let's simulate this and call pepper with sys, exp, and see how it looks like. I need to plot it. That's why it's not showing up. Plot p spec 1. Voila. So we see three groups of line pairs. The splitting is at low field is largest. The splitting in the middle field and the splitting at high field is the smallest. We see a little bit of simulation, what we call simulation grass here. These are not physical features. This is just an effect from not having enough orientations when you do the powder averaging. But we'll get to that. But for now, this is good enough. And now, so right now, this assumes that the G tensor, given here G, and the A tensor, given here with A, they are collinear, which meaning the X direction for this G value is the same as the X direction for this A value. Right? One way to think about it is each tensor has some sort of ellipsoid, kind of a potato. And if these ellipsoids are oriented the same way, then they're called collinear. And that's what we have right now. Now, in reality, in molecules, these tensors all they're tilted relative to each other, and you might want to specify that tilt. And that can be done with for the hyperfine tensor with something called A frame. So sys.A, because it's a hyperfine coupling, and then frame to specify the orientation of that tensor relative to a molecular reference frame. So the A frame, let's say 0, 0, 0. That's basically saying it's aligned with the G frame, aligned with the G tensor and with the molecular frame. And these are the three numbers of the so-called Euler angles. And they are in radians, not in degrees. Okay, so if you press Control Enter, nothing changes, right? Because if you don't specify an explicit orientation, everything's assumed to align with the molecule. And so EasySpin implicitly has this notion of a molecular reference frame, which is kind of an XYZ frame system that's attached to the molecule in a fixed orientation. So if you turn the molecule, the frame rotates with that molecule. Right? And what you do when you specify these frames here for A frame is you specify how your tensor is oriented relative to that molecular XYZ axis, the molecular reference frame. But more about that in the next session. Let's just now tilt the A tensor and observe the spectral changes. I'm going to copy paste this here. I'm going to now change the first Euler angle to pi over 2 and simulate a new spectrum with that and plot that together with the first spectrum. Control Enter, and voila. You see what has happened is that some values change, right? The orientation of the hyperfine tensor changed so that a different hyperfine splitting is now observed for a given G value. So this is how tensor frames work. Another thing we can do is, let's go back now and we can get transitions out separately. And, that is called opt.output equals separate. Now let's look how this looks like. Pepper, we're going to just call pepper again with whatever system we just have defined, and look at, we have to also feed in the options now. Again, the third input is always simulation options. In this case, it's just telling us that the output should be in separate transitions. What you see here now, previously we had one spectrum that had these 6 features, right? 2 in the low field, 2 in the middle field, and 2 in a high field. Now we're getting at least, 1, 2, 3, 4 separate spectra. So these spectra are this different separate transitions in the EPR spectrum. The 2 intense ones are the allowed ones. Let's see if we can pick them out. Here's the red one, and then we have the orange one. But we also have a blue and a purple one, and those are very weak. If you look, we can zoom in. Those are very weak. These are forbidden transitions. So this shows you that EasySpin always, when you use Pepper, it always simulates the allowed and the forbidden transitions. Because in some cases, these forbidden transitions are actually quite intense. So that's how you get separate output. Now let's revisit this problem of orientational averaging. Let's go back to a much simpler system to make this more clear. And the simple system here is a G value, an axial G value of 2, 2, and 2.5. Some convolutional broadening, we're at X band, and we're looking at the powder spectrum. If I run this, I'm getting a nice axial spectrum, but if you zoom in, you can see there's some wiggles. These wiggles are what we call simulation noise or simulation grass, and it's a problem. It appears when you don't have enough orientations in your averaging. Because in order to simulate the powder spectrum, what EasySpin does, it simulates spectra for many different orientations and adds them all up. So how to increase the number of orientations? That's a simulation options. And the option is called opt.n knots. The number of knots on a sphere. And we can start out with a very small number to see how bad it can get if you have only 10 orientations. So I'm writing 10 here, and I'm adding the third input to Pepper. Third input is always simulation options. Control Enter. And what you see now with 10 orientations, we get some artificial peaks throughout the entire spectrum. Let's increase that. Let's go from 10 to 100. And you see in this case with 100 orientations, we're very much converged. There is not a hint. Maybe there's a tiny, if you zoom in really close, you can still see there's a little bit of simulation noise, but that should be gone as soon as you go to like 300 knots. But as you probably might guess, using more, increasing the number of knots also increases the simulation time. So always try to optimize the number of knots. Keep it at a minimum. That gives you a smooth spectrum without wasting simulation time. You don't need more orientations than necessary. So 100 is probably a good choice here. You can see EasySpin is able to simulate a full powder spectrum with just 100 orientations. In your sample, you have probably 10 to 12 or 10 to the 13 different orientations from your 10 to the 13 molecules. But 100 is sufficient to get a smooth spectrum. Okay, field and frequency as the next topic. So Pepper simulates a solid state field swept spectrum, but it can also do a frequency swept spectrum. Let's take the examples from above. But now instead of just specifying a fixed microwave frequency, we can specify a fixed field. X.field, let's put in 350 millitesla. And now if you call Pepper with this particular sample, with this particular experiment, it will actually simulate a frequency swept spectrum for a fixed magnetic field. Control Enter, and voila. We see it now. The x-axis is a frequency axis in gigahertz. And if you're at 350 millitesla, the spectrum for this particular sample goes from 9.7 gigahertz all the way to 12.2 gigahertz. Now, of course, nobody has this type of X-band spectrometers, but you know, there might be some broadband spectrometers that do frequency sweeps. That actually there are, and it's also very useful to look at frequency swept spectra if you're doing pulse EPR measurements, for example, ECM or ENDOR or DEER, because those pulse EPR experiments are done at constant magnetic field. And this frequency swept simulation lets you look at the EPR spectrum that you actually have in your sample for that fixed magnetic field. Okay, as you can see, we see some steps here. These steps are not simulation. They are simulation graphs, but we have a problem. Our line width is too narrow, unrealistically narrow. And the reason is that LWPP for a frequency swept spectrum is now interpreted in megahertz. So you have to change that to a much larger number because half a megahertz is an unrealistically small broadening. So let's change that maybe to 50 megahertz. If you run that again, now we get a more realistic broadening in your frequency swept spectrum. So finally, for the solid state simulations, one more thing I would like to mention is the algorithm that's underlying it. Just like for garlic, for liquids, you have a choice of which algorithm to use. And by default, Pepper uses the slowest but most exact one. But you can reduce the theory level to a more approximate treatments to speed the calculation up. And if you have a lot of nuclei in your spin system, then this is sometimes required to make it workable on a computer. But you always need to check whether the approximation is actually valid or not. So let's start out. Let's do, what did I do here? Spexis. I think we can take the same spin system. Let's go back. Let's take this spin system here. Clear, and now let's actually go down to S-band. which is about 3 gigahertz. I'm going to now explore several simulation methods. Opt.method is again the field, and the most accurate method is called matrix because it performs matrix diagonalization of the spin Hamiltonian matrix. Let's then simulate this. We spec 0 equals pepper and provide the sample, the experiment, and the simulation options. Then we're going to copy paste this and just change the theory level twice. We're going to use perturb 1, which is first order perturbation theory, and perturb 2, which is second order perturbation theory. We call this spec 1 and spec 2. Finally, we're going to plot all of this, B spec 0, B spec 1, B spec 2, and add a legend for matrix, perturbation theory 1, and perturbation theory 2. And if you run this, in this particular case, you don't see a lot of difference. But if we start adding nuclei, you will see that the treatment will be very much different. And you need to explore, if you need to reduce your set simulation time because you're running out of time in memory, you can go from matrix to perturb 1 and or perturb 2. But then you always need to at some point check whether your perturbation assumptions are valid. So this concludes a brief initial overview for solid state EPR. In the next session, we'll talk a little bit about frame orientations and Euler angles. And in the session after that, we'll swing back to solid state EPR simulations. And for now, please look at the script, go through the exercises or start looking at exercises or just take a break. I'll see you back. It is now 9:52. I'll see you back at 10:10, which is in about 18 minutes. Until then, bye. Welcome back to EasySpin Academy 2020. This is session number 5, and this session will be about coordinate frames, which is really important when you do solid state EPR. So when you measure EPR in a solid sample, orientations play an important role. Molecules have fixed orientations, and within the molecules, the different interaction tensors also might have different orientations. So it matters how the sample is oriented in the spectrometer, and how the spin center is oriented in your sample, and how the tensors are oriented within your spin sample. So in this session, we're going to go over some of the basics of how EasySpin handles orientations. So we're not going to do any simulation, we'll just talk about the various tool functions that are there to support kind of thinking about and visualizing orientations. Okay, first of all, we need to talk about Euler angles. In order to specify the orientation between two different objects, there's several ways to specify that. And the one that EasySpin uses foremost is a triplet of Euler angles. And for example, let's take, actually let's go to the Euler angle documentation first. So if you go to the documentation, there is a documentation EPR reference is called rotations and Euler angles. So if you go there, you can see a summary of how EasySpin defines rotations. Euler angles are defined by 3 successive orientations around canonical directions to transform one coordinate frame, XYZ frame, to another. Okay, and this picture shows exactly how these angles are defined. These angles are called alpha, beta, and gamma, and in EasySpin, you should give them in radians and not in degrees. And these alpha, beta, gamma angles are then converted with an equation to a rotation matrix, which is a 3x3 matrix that specifies the angles between each pair of axes of the 2 coordinate frames. So let's go back. So let's define some angles. Let's say alpha is 20 degrees. We need to convert them to radians though. So one way to do that is just to multiply it by pi and divide it by 180. Or the alternative, which I'm going to write out here as well, is use degree to radian, which is a conversion function. Those 2 forms are fully equivalent. I tend to use the first form. Beta equals, let's take 40 degrees. Let's annotate this as these are radians. And gamma, let's take as an example 80 degrees. Now, in order to calculate the rotation matrix associated with these 3 Euler angles, you've used the function E-rot, where E stands for Euler rotation. So alpha, comma, beta, comma, gamma, and assign the result to R. If you run this and press Control Enter, and we not put a semicolon at the end of the line, we should get an output in the command window. And here it is. Here you can see you're getting a 3x3 matrix that contains values between -1 and +1 that are used to transform one frame to the other. So this is called a rotation matrix. Each element of this rotation matrix is actually the cosine of the angle between the 2 axes. So you have 2 frames. That's called the first frame A and the second frame B. If you take the arc cosine of R and convert it back to degrees just for easier looking at and run this, you can see that here, you can see that the angle between the x-axis of frame A, which is the first row here, and the x-axis of frame B, which is the first column, is 102 degrees. And the angle between the 2 z-axes is 40 degrees. Now, how are these rotation matrices used in EasySpin? So if you define a G-frame, right? We've defined a G-frame like this, sys.G-frame, and then you give 3 Euler angles. Okay, we're gonna just do this now without the sys. We're not gonna do any simulation. Let's call it G-frame. Let's put in some random values, maybe the same as before, 20, 40, 80, and convert that to radians. And then let's get the rotation matrix for the G tensor. Rg equals E-rot of the G-frame. And let's clear out. Actually, let's start with a new section, clear and clean the command window. Let's define a diagonal G tensor which is just, let's say, 2, 0, 0, 0, 2.10, and 0, 0, 2.15. And now the transformed G-tensor is obtained by rotating the diagonal G-tensor with this rotation matrix. This done by just RG times the G diagonal times RG transposed. So the dot prime or dot quote indicates or tells MATLAB to transpose the matrix, basically flip it around so the rows become columns and the columns become rows. Okay, let's clear out the comment window first. And now let's look at the output. The first output is the rotation matrix that is calculated from the Euler angles you give in G-frame. The second one is just a look at the actual diagonal G matrix with the X direction, the Y, and the Z direction of the G-tensor. And the third is now the rotated G-tensor, or transformed into that frame that corresponds to the Euler angles. And as you can see, it's still mostly diagonal. It has 2 point something on the diagonal, but it has small off-diagonal elements. Right? And this kind of tells you that the tensor is now rotated relative to the molecular reference frame. So this is how you transform a tensor. Let's say now you have given a rotation matrix. Let's let's call it R, right? I cleared it out, sorry. Let's get another, I'm gonna define a new R matrix. I'm gonna select all this code here and just run it by pressing F9, or on Mac it's Shift F7. So F9. Now we've got a new R matrix defined. You can now back calculate the Euler angles from the R rotation matrix by using a command called eulenc. And if you feed that with R, I'm going to run this section again. Voila, you get back 3 numbers that are rough around the order of 1, but these are in radians. So we want to compute them back to degrees for better visualization. Multiply it by 180 and divide by pi. And voila, we can be getting our 20, 40, and 80 degrees back that we put in first. So this is how Euler angles work and how they relate to rotation matrices and how you can rotate a tensor. Or this is also how EasySpin internally rotates tensors. So for example, if you specify a spin system, let's say with G value 2, 2.05, 2.2, and say you also have a hyperfine tensor in there, let's say 10, 20, and 50. If you don't give any frame rotations, these two tensors are considered to be collinear. Now you could specify a tilt for, let's say, the A tensor. It would write A frame and then give some numbers here, and I'm just going to put in some random numbers. Okay, this will tell EasySpin that the hyperfine tensor coupling is actually rotated by the second Euler angle of a value of pi thirds relative to the molecular reference frame. So an important concept is in EasySpin is the molecular reference frame. So everything in the spin system is relating to that XYZ system, which you can just picture yourself however you want within the molecule, but it's fixed, right? And we have specified an A frame, which means the A tensor is tilted relative to that molecular frame. We have not specified a G frame, so which means the G is actually parallel or collinear with that frame. Basically, that's equivalent to saying sys.G frame equals 0, 0, 0. It means the same thing. If you don't give a G frame, it's assumed to be 0. So that's basically how these tensors are specified for a spin system. Now, this is all very abstract, right? Euler angles and rotation matrices are very math heavy, and it takes a while to actually make sense of them. For this, then now new in EasySpin 6, there's a rotation matrix viewer. And to get it started, let's take these 20, 40, 80 and call a function called rotview. And this function is only available if you downloaded the latest EasySpin 6.0 development version, which was published yesterday. So it's called 6.0.0/-dev26. So let's feed it some Euler angles. Actually, you don't have to feed it Euler angles. We can adjust them later. Let's run rotview. Rotview will fire up a small interface. It looks like this here. That allows you here in the bottom left to adjust the Euler angles. So you can change that, and we'll actually change the rotation, alpha, beta, and gamma. You can select the scenario you want to look at, either the G frame or A frame or D frame. Well, let's stick with it. Let's go to the A frame. And then it also allows you to show a tensor ellipsoid or not. Right? So let's look what it means. You can see here in dashed in red, green, and blue, the molecular reference frame, abbreviated with M. So XM is the x-axis of the molecular reference frame, and then we have YM and ZM. That's the first coordinate frame. The second coordinate frame is the frame of the tensor, of the in this case, the A tensor. The A tensor is kind of symbolized by this ellipsoid here, which kind of has three different lengths in each of the three axes. And you can see there its principal axis system shown in red, green, and blue. Red, again, is the x-axis of the A tensor. Then there's YA and ZA. And now basically you can visualize how this tensor is tilted relative to the molecular reference frame with these particular values of the Euler angles. And you can change them. And let's go back to a very simple case here. Let's say alpha and gamma 0, and beta is 20 degrees. So you can see that the molecular z-axis and the tensor z-axis are at an angle of 21 degrees here. Then on here on the top, you'll see a 3x3 array of numbers. These are the angles between the axes, as I've shown you before. So for example, the top, actually let's change the angles a little bit. So the top value here, which says 45 degrees right now, is the angle between the two x-axes. So between the molecular x-axis and the tensor x-axis. So that if you just measured the angle from here to here, it will be 45 degrees. So this is a little Euler angle and rotation matrix explorer that hopefully is very useful to understand this fairly complicated aspect of solid state EPR a little better. This function is pretty new, and we still have some plans to improve it. So keep updating your EasySpin installation to get the latest for this function. So how are we doing time wise? 10:22. We're good. 10:40. Another new feature of EasySpin 6 is very useful if you are dealing with dipolar coupling tensors. For example, if you want to figure out the tensor for two electrons are coupled in space, or for an electron coupled to a proton. So I'm going to make a very simple example here. Let's say two electrons are exactly 1 nanometer apart, and they're apart from each other along the z-axis. So then the distance between those two electron spins is a vector, can be written as a vector, and if they're along the z-axis, both of them, then the x is 0, the y is 0, and the z is 1 nanometer. So this r is the vector that goes from one electron to the other electron. Now, if you want to get the dipolar coupling tensor, all you need to do is call a function called dip tensor. It stands for dip, for dipolar tensor. Then you first specify what's the first spin. It's an electron. And you need the second spin. It's also an electron. And then you have to specify the distance vector. Now, actually, let's clear and CLC at the beginning here. Voila. And then run this in the command window. And voila, it gives you the full dipolar coupling tensor. Now, if this were not an electron-electron coupling, but an electron-proton coupling, you just change one of the e's to 1h and run that again, and see that you get couplings that are below 1 megahertz. The units that this gives back is always in megahertz. So that's another little utility function that allows you to calculate dipolar tensors. If your R vector, the connection vector between the two spins, is like tilted or points somewhere else, you can just enter that here. You just enter a slightly different vector. If you get the dipolar tensor, then it will have a 3x3 matrix where all the numbers are non-zero. There's a few other things that are useful to have with orientations. For example, a coordinate frame that's used often and very much in EPR are the polar coordinates. So where you have two angles, you specify the direction of a vector. And what you do is you just turn it down from the north pole, you take a vector that's pointing north, turn it down by a certain angle, and then I rotate it by a certain angle. This is equivalent to longitude and latitude on Earth. And you can convert the vector to angles and the angles to vectors using two functions that are called ang to vec and vec to ang. Okay, let's first start with the angles, right? Let's say phi is 10 degrees. As always, we have to convert to radians, the canonical angle unit in EasySpin, and theta is 30 degrees, so radians. Then if you can get the actual associated vector by just using ang to vec and then feeding it phi and theta, right? And so if you run this, let's clear the command window and you're pressing Control Enter, voila, you get the vector that points exactly in that direction. And if you're gonna get reverse, use the function vec to ang. Those are some basic things. I think the last thing I wanted to show in this demonstration is a utility that's useful for those of you who are doing crystal studies. So people who have samples that give spectra that depend on how you rotate your sample tube, right? And that applies to single crystals or also to oriented films. And EasySpin has, especially EasySpin 6, has now much improved capabilities to describe these samples. Underlying that is this whole mathematics about rotation matrices. So here's a utility function that helps you rotate something around a specific axis. So let's say we've got some frame. Where's my frame here? Okay, let's some initial frame orientation. I'm just copying that from my prepared script here. 3 Euler angles, right? 3 Euler angles specify a certain frame orientation. Okay, next we gonna define some rotation axis, and let's take the lab x-axis as rotation. EasySpin uses a fixed frame definition for the lab, and well, maybe I should show that right away. So if you go to the documentation and you go to the basics section of the user guide, there is one section called coordinate frames. That is quite important because it tells you how the various frames are defined, the convention for the frames in EasySpin. For example, there's the lab frame. What is the lab frame? That's the frame in your spectrometer, right? It has 3 vectors, the x and the y and the z. And it's of course a universal convention that the z-axis is defined to be along the static field. So if you have like a big magnet for an X-band EPR spectrometer, it points horizontally. I think also in the benchtop spectrometers, it points horizontally. And then if you have just a standard EPR machine, usually the oscillating microwave magnetic field goes vertically. And in EasySpin, that is treated as the x-axis of the laboratory frame. And this vertical axis is also the axis around which you typically turn your sample. That's your sample axis, right? And so, but there's crystal frames, molecular frame, tensor frames, and you can look up here in the documentation how they are defined, the word by convention, the x, y, and z direction for these quantities are. Okay, so let's go back. Let's define the x direction. 1, 0, 0. This is lab fixed x-axis, right? That's equal to the sample axis typically, right? In a standard spectrometer. And let's say it's specify a rotation angle like 20 degrees, again radians. And now if you basically want to rotate this frame specified by ORI 0 by this angle rho around this axis, for example, if you just do a single crystal experiment, what you do, you just say ORI equals rotate frame, and you feed the original orientation, Euler triplet, then the rotation axis, which is the x lab axis, and the rotation angle. Control Enter, and voila, you can see that it spits out the result of the rotation, again in the form of 3 Euler angles. So these are just some simple tools to handle orientations. Most of the times you don't have to use these tools directly if you just want to simulate something. But it's important to be aware of them, that they exist, and especially the new visualizer allows you to get a better feel of what these angles actually mean. So this concludes the session on orientation and coordinate frames. I encourage you to look particular at the documentation. Just to reiterate, there's two places to look at. There is the coordinate frames section in the basics, and then there is a rotations and Euler angles section in the EPR in the EPR reference part of the documentation. With that, I'll send you off to explore this or just take a break. We will be back for the last topic session of the day at 10:50, which is in 20 minutes. And see you there. Welcome back to the EasySpin Academy 2020. This is session number 6 of the first day. We're going to look a little more into detail into several other features of solid-state EPR simulations. So this is the last topical session. The next session will be a general questions and answers, where we'll pull some of the questions on Slido. And if you have questions you would like to answer us in the Q&A session, please post the questions on Slido or upvote questions that you're interested in, and we'll look through Slido in the Q&A sessions. All right, so for this session, we'll concentrate again on solid-state EPR. In the previous session, we've seen some of the basics, and now let's explore a few more features. First of all, high spin systems. Let's take a triplet system, so sys.s equals 1. We're going to add some zero field splitting, D, say 1000 megahertz for the D value and 130 megahertz for the E value, and add some line width broadening, say 2. Then we'll simulate the X-band spectrum. Let's take 10 gigahertz for now, and just specify the sweep range, 300 to 420 millitesla, for example. And Pepper can easily simulate this high field, or these high spin systems without any additional input except spin 1. And there you go. Here you see a rhombic triplet spectrum of a thermally polarized triplet. But as you know, as many of you know, for a high spin system, you might also expect a double quantum transition, a half field signal. Let's see if that's there. So all we need to do for this is we need to change the range to extend down to the field value where we see the half field transitions. So let's go down to about 100, maybe 150 should be sufficient. So if you run the simulation, and voila, you have it. Around G equals 2, you see the single quantum transitions. These have delta ms equals 1. And down at roughly half field, you see a much weaker transition. That is due to the delta ms equals 2 transitions. And these are nominally forbidden double quantum transitions, but since there is Zeeman state mixing going on, they have appreciable intensity. So for high spin systems, since Pepper EasySpin use exact matrix diagonalization, you will see all these semi-forbidden or semi-allowed transitions, and they can get quite complicated if the electron spin quantum number is very large. So a triplet is just the simplest possible high spin system to demonstrate. Another important thing is temperature. Again, let's take the spin system from before. Again, our triplet with a rhombic D-tensor. Well, let's make the line a touch narrower. Let's take the same frequency, maybe just focus on the single quantum transitions between 300 and 420. And now let's add a temperature, exp.temperature. Let's run it at 2 Kelvin. So at really low temperature, and let's see what happens to the spectrum. So right now, I haven't run it yet. You can see the current spectrum. It looks nice and fairly symmetric. If you run this at 2 Kelvin now, I'm going back to this section here and pressing Control Enter or Command Enter. You will see that there's some slight intensity differences. For example, this line is more intense than this line. If you go even lower in temperature, it's an expensive experiment, but with EasySpin you can do it. You can see that the thermal polarization of this triplet becomes stronger and stronger. If you change the sign of the D value, you put a negative in front here, then the D-tensor is negative. That swaps the energy levels around and will also swap around which levels are going to be populated in this low temperature range. Pressing Control Enter shows that now the spectral shape is inverted. So this is now the weaker transition than this. So EasySpin takes care of all the Boltzmann populations and calculates them accordingly. And we can of course always show the absorption spectrum by setting x.harmonic to 0. Voila, here's the absorption spectrum. And we might want to look at the two transitions separately by saying opt.output equals separate, and include that as a third input to Pepper. I misspelled that, separate, voila. And now you can see that there are two transitions, two powder transitions, and one is much weaker than the other due to the thermal polarization. Next thing to briefly mention are multiple components. So you can have one pepper call and include multiple components at the same time. So let's start out clearing everything and define a first spin system with like G values 1.95, 1.98, and 2.05, and some broadening, just convolutional broadening in millitesla. And let's then take a second system that has slightly different G values. You know, that's something you often can encounter if you're looking at catalytically active species, like intermediates of catalysts or in enzymes. Let's say they say 2.17 or so. And let's make this line a little broader. So you can simulate the spectra of these two at the same time, if they're in the same sample, by a single pepper call. Let's define the microwave frequency and the field range, 300 to 400 millitesla. Gigahertz for the microwave frequency, and it's called pepper. And now you have to use curly braces, which indicates a cell array. In MATLAB, you have different types of arrays for those who are new to MATLAB. First of all, there's numeric arrays, where each element in the array is just a number, right? Then you can have cell arrays, which are also arrays, but instead of just a number, you could have anything in that array. You could have in the first entry, you could have a number. In the second entry, you could have a string. In the third entry, you could have an entire matrix, and so on. So a cell array is kind of allows you to build buckets and lists and collections of different things. And here, as for a cell array, you have to use curly braces instead of square brackets. So since we're going to put two spin systems together, and each spin system is a structure with fields, we have to use curly braces. So sys1, sys2. That makes a little cell array with two elements, where each element is one of the spin systems. And comma, and then the experiments. And that's it. If you now press Control Enter, sys2, I have to define the numbers here. We have sys1 and sys2. Voila, and now you can see we have an overlap of two spectra. We see this one here with a peak here, here, and here at high field. And then we have the other one, which has sharper features. This is now a 50-50 mixture, but you can also modify the relative weights, so the relative concentrations of the two species, by adding a field called weight. And let's say the first one is a 30% abundance, and the second one has a 70% abundance. Now if you look at the spectrum again, I write this at 50-50. If I run it again, it's now 30-70. I could reduce that to like 10-90, right? And then you can slowly see that one component is vanishing relative to the other. So this allows you to simulate mixtures in one go with one call. And an important thing to reiterate here is that pepper is spin calibrated. So if you say 70% of one spectrum and 30 from the other, it truly means that 70 out of 100 spins are from the first species and 30 of the 100 are from the other. So you can actually use this to quantitate spectra relative to each other. So for example, if you have a solution of a radical with unknown concentration, but you add another radical with a known concentration, and you get overlapping spectra, if you're able to simulate them, you can read off from the EasySpin weights, you can actually read off what the relative concentrations are. So this is concerning multiple components. Next, important topic, crystals. For some of you, this is the bread and butter, especially if you're looking at defects in solids or small molecule crystals. So EasySpin is fully built out to handle single crystal simulations, and we'll do a very brief overview here. Let's start with a very simple spin system, some spin 1/2 electron with a G tensor of 2, 2.1, and 2.2, and again some convolutional broadening of 0.5 millitesla. Now we're going to add a microwave frequency of 9.5 gigahertz and a range as usual, maybe 300 and 350 millitesla. And let's simulate the powder spectrum. First, we're going to ask Pepper to return us the data instead of just plotting them. Right, and probably should clear the figure at the beginning so we don't have that previous plot. I'm going to run this now. Voila, and everything's clean. Okay, next, we're going to actually specify a crystal orientation, right? If you do it on a crystal, you have to orient it in a spectrometer, and this orientation needs to be communicated to EasySpin. It's done by a exp.crystal orientation equals, and then you just have to give a triplet of Euler angles. Say 30, 20, 40 degrees. We have to convert it to radians as usual. Okay, and now let's simulate the spectrum again, this time the single crystal spectrum, because we added exp.crystal orientation. Let's see how that looks like. We're going to probably just make two subplots, subplot 211, where we're going to plot the powder spectrum is spec 0, and subplot 212, where we're going to plot the crystal spectrum. Okay, I'm going to run this now and let's see what happens. Okay, now on top you can see the powder spectrum. It extends most of the field range. And on the bottom you can see a single crystal spectrum with just a single absorption line. And this is determined, this is a function of the orientation in the of the crystal in the frame. So if I change one of these angles, then the orientation, the resonance of the crystal changes, the resonance position. Now, the molecule within the crystal is still assumed to be aligned. So the crystal itself is associated with an XYZ frame and the spin carrying molecule as well. And what you can do, you can specify the relative orientation between the molecular frame, so where the spin bearing molecule, and the crystal frame, which is related to the ABC axis of the crystal. You can do this with exp.molframe. And let's say we're going to give this in radians directly now. Again, you give 3 Euler angles. And if you run this, of course, you will get a different resonance position, because now I've tilted the molecule within the crystal relative to the crystal faces and crystal morphology. So crystals, of course, have spatial symmetry, not just rotational symmetry. As you know, in EPR, it doesn't matter, whether the molecule is on the left in your sample tube or on the right. EPR is insensitive to translations. But in crystals, these needs to be taken into account because they lead to different space groups, symmetries of the crystals. So there's 227 different space groups for crystals, and they result in a multiplication of those crystal absorption peaks, because the same molecule could occur in different orientations within the crystal. And in order to specify a space group for a crystal, all you need to do is to add exp.crystal symmetry. And then just give the number of the space group. 1 is the easiest, and that's the one that it assumes by default. And then there's just one line. But let's just pick another one. That's a space group number 50. And then you get 2 lines because it has a higher symmetry. Or space group 100, you get 4 lines. Or if we go to the highest symmetry space group 227, right, you end up with probably about 12 or 16 lines, probably 12 lines. That can make this a little narrower, then we get better resolution. There you go, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You get 12 lines, and these 12 lines are due to paramagnetic molecules within the crystal that have 12 different discrete orientations. And these orientations and how they relate to each other are specified with this crystal symmetry space group. So now let's say you have this crystal, and let's go back to a simpler space group again, so we have not too many lines. That's only 2, or let's say it gets 4 lines here. Now let's just say you have your crystal in there and you want to rotate the crystal. Right? And all you need to do a little rotation is you have to define which lab frame axis you're doing the rotation around. And if you recall, the lab frame is defined such that the z-axis is the magnetic field. So that's horizontal typically. And the microwave oscillating magnetic field is vertical in a typical resonator. And that's also the axis of the sample tube. Right, so the x-axis of the lab is going to be the sample tube, and we're going to rotate around that sample tube axis. Okay, so let's define, I'm gonna do this here. XL, lab frame axis of 1, 0, 0. Well, that's the direction of X in the XYZ frame of the lab. And then let's rotate it by 10 degrees. Again, it needs to be in radians, because that's the conventional angle unit in EasySpin. And now to tell Pepper or EasySpin to rotate the crystal by 10 degrees around the x-axis, you just have to say x dot sample rotation equals, and then a cell array with the rotation angle, rho, and the rotation axis, XL. That's all you need to do, and you can just basically step the angle through and see how the spectrum changes. This is new in EasySpin 6, so if you're using EasySpin 5.2, you can't do this, and it's much more complicated in the old EasySpin version. So if you're using if you're doing crystal simulations, I encourage you to update to EasySpin 6. All right, so what happens now? Let's start, see where those 4 peaks are. 10 degree rotation moves those peaks somewhere else. And if you want to explore how this changes, there's a little neat feature of MATLAB. If you have a number and you want to change it and rerun this section, you just right click on it, and then the first entry in the local menu will say increment value and run section. If you click on that, it opens a little menu where you could say, okay, I want to add or subtract degrees or values from this, and that say 5 degrees, and if I click on the plus, it will increment that number by 5 and run the whole section. So while I do this now, look over at the spectrum and see what happens. Plus 5, 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 and so on. As you can see, as we rotate the sample, these resonance lines move around, and we have 4 different orientations within the crystal, and each of these orientations behave differently. So this is how you do crystal simulations. Just the basics. Next thing, it's 11:07, 11:30, 11:20. Okay. Next thing, parallel mode EPR. So sometimes, especially for integer spin system, you will not be able to observe a perpendicular mode X-band EPR spectrum, in which case it's good to simulate parallel mode. EasySpin supports that out of the box. So let's take like a spin system. Let's take S equals 2, which is which is a spin quantum number where you typically don't see any X-band data. So this could be typically for example, on high-speed iron 2. Let's add a really large zero field splitting, let's say 300,000 megahertz, which is 300 gigahertz. And let's keep it slightly rhombic, so with an E value of 0.1, E over D. So again, don't forget to specify tensor values, principal values in megahertz, even if they're very large. sys.lwpp, some broadening, just for simplicity. Then let's go to a standard microwave frequency, X-band. Now let's sweep the full magnet. Let's say we have a smaller magnet and it goes up to like 600 millitesla. And let's go simulate the spectrum. And by default, this is actually using perpendicular mode EPR because that's the normal vanilla EPR we're all doing. And you can be explicit about that by saying x.mode equals perpendicular. And then now let's simulate the same spectrum using parallel mode. All you need to do is change x.mode to parallel, and it will internally switch the way it calculates the intensities, then the transition matrix elements, and that then gives you the parallel mode EPR. We can plot the 2 spectra and see how they look. Control Enter again runs this whole thing. It's taking a little time, and voila, I should have probably deleted this figure here. So you can always delete a plot by clicking on the figure, then going to the figure ribbon menu and clicking on that little cursor. And then you edit plot mode which allows you to select individual things within the plot and then press delete just to remove them. Or I can remove the entire axis. I can click here and I can enlarge this. Voila. Okay, now you can see we've got in the perpendicular mode spectrum in blue and the parallel mode spectrum in red. The parallel mode spectrum is much more intense. What you see are some kind of oscillatory features. This is again simulation noise. We don't have enough knots. So what we need to do is we need to increase the number of knots. So up dot n knots equals, let's try 31. And include options in the two calls and run that again. And if you look here at the bottom left, in the very tiny thing at the bottom, will say busy. That tells you that it's running. Also, if you're on the editor panel, it will show a pause button here instead of a run button, and that will tell you it's running. Okay, we still have the number of knots is not sufficient. Let me double those to 61 and see if you get a difference. It's running. As you can see, if you have a higher spin system and you have a lot of orientation, the simulation can actually take quite some time. We'll wait until it concludes here. Voila. Now it is concluded, and you can see that we still have some oscillations, but they're much smaller. The fact that you still see oscillations means you just have to increase the number of knots further. You know, if you're only interested in this low feature, you might disregard them for now and just focus on this. But then if you want to simulate a publishable spectrum that's smooth and simulated, increase the number of knots. You can also see that the parallel mode or the perpendicular mode spectrum in blue is affected much more. It's not as smooth as the parallel mode. So if you just look at the parallel mode, again going to the figure window and deleting the perpendicular mode here, grab this. You can see that's actually fairly smooth. If you zoom in, you will see a little bit of simulation noise of incomplete averaging. But that's probably totally bearable, even if you go into a least squares fitting analysis, which we're going to talk about a lot more tomorrow. So the last thing I'd like to mention in this second session on solid state EPR are spin polarized triplets. Often there is a system when you photo excite them into an excited singlet state, they transition over into an excited triplet state via intersystem crossing. And these are, of course, EPR active species, with a difference from the standard triplets that they don't have thermal polarization, but they have non-thermal populations on their energy levels. And this can be done in EasySpin fairly straightforwardly. So let's take this a little further up here. Let's clear the figure and define a triplet. So that's a spin once system. Let's put a G value of 2 and give it a D value of like 342 megahertz with 21 for the E value. These are the actual numbers for the excited triplet state of C60 of Buckminster-Fullerene. Now, in order to specify these non-equilibrium populations for a spin polarized triplet that came into being through a singlet triplet intersystem crossing, use sys.pop, where pop stands for populations. And these three population numbers, we can put 1, 0, and 0 in there. These refer to the energy eigenstates at zero field, because that's typically how these states are the ones that are being populated by the intersystem crossing. And these numbers don't add up to 1. And they will depend, which numbers they are, depend obviously on which system you're looking at. So, add some line width, define the frequent day experiment, some numbers here, 310, 350, and x dot harmonic equals 0, because we're going to look at the absorption spectrum first. So if you are familiar with this and you're using EasySpin 5.2, you will notice that this is actually new. This is new in EasySpin 6. It's a much cleaner interface than in the old version, where this was mangled into the temperature field. Okay, let's see how this looks. I'm pressing Control Enter, and voila! Now you see this is the absorption. There's a zero harmonic spectrum. So any positive intensity is absorption, and any negative intensity is emission, right? And you can change the populations here, and you'll probably see some changes in this spectrum. Voila! And you can even look at the transitions separately. So say opt.output equals separate. Put that opt in as a third parameter, and run again. And now you can see these are two transitions. It's a triplet, right? So there's 3 levels, and you can have 2 transitions between adjacent levels. And depending on orientation, each of those transitions is either absorptive here in the high field edge, or it can become emissive on the low field region. So this is valid for so-called intersystem crossing triplets that come from a singlet to triplet transition. If you have triplets that are generated from radical pairs, then the mechanism is slightly different, and you can't use cis-pop directly. But you can find more about this in the documentation. So these are a few additional topics for solid-state EPR. In general, please always go back to the documentation. It's fairly extensive. There's a user guide on doing solid-state EPR simulations. There is a separate one for single crystal simulations, and yet one more on spin polarized systems. And you might also want to look at the reference page for Pepper, which is kind of, I would say, the core function of EasySpin. It's been around the longest. I think with this, I'm at the end of my plan for this session. I think we're doing good time-wise. So the next session will be a Q&A session. And I think Stefan Pribitzer has already compiled a few questions he found on Slido, and I'll also have a look in the next couple minutes, and I'll see you back then at the Q&A session, where I also will show you how to access the happy hour space at GatherTown. Until then, enjoy your break or look at the documentation of the exercises. Bye. Welcome back to the last session of today's EasySpin Academy 2020. This is not a topical session. I'm just going to go over some of the questions that appeared on Slido over the last 5 sessions or 6 sessions. Before that, though, I'd like to remind you of a few things. First of all, I want to mention again the t-shirt campaign that we're having. In fact, I think already 15 t-shirts are committed. We are not making any profit of this. Any profit from these shirt sales go to a foundation. So if you want a t-shirt from this academy, go to bonfire.com, and I think the link has been posted in Slido to get one. The second thing I would like to show is the happy hour space we're going to have starting in half an hour. And the link is on the Academy website, and you should have also received it in your email. Here we are. So I just logged in. I had to give myself a name, which I already did ahead of time. Basically, this is a large space where you can see where you can see yourself in the center, and you can use your cursor keys to walk around. And so, and then here in the center, you will see indications of where to go. So this is basically a series of rooms. There's a central plaza here. And at the bottom, you can look at the mini map of the space. This is a central plaza, and there's several white doors. The ones on the left go to the so-called easy bar, and the doors on the right go to the spin bar. And then there's gateways on the top and on the bottom, which lead to the north and the south beach, and to a bonfire and to the dock. And then in addition, we have a pepper bar and a salt bar here. And we have breakout rooms for like smaller rooms that are up here. There's 5 of them. And there's another 5 rooms that are down here. The rooms here on top are numbered by spin quantum numbers. So room 1/2, room 3/2, room 5/2, and so on. And the ones here at the bottom are have some topic names like nitroxides and pulse EPR. So when you join, just go in and wander around using this mini map. You can modify your avatar again here at the bottom by click on change character, and you can change your shirt and what character you want to look like. And as you walk, and so I'm going to go over to the easy bar. As you walk, you will see people, and whoever is in your range will show up with a video. Voila, and here we are in the easy bar, and you can see, if people are seated on any of these tables, you will be able to talk to the other people. These dots are, whenever you see these dots, these are so-called private spaces, which means you can have a conversation just with the people who are sitting at this table and nobody else can hear you. If you're not in a private space, everybody within a certain radius will be able to hear you and see you. And you can change the radius of your personal space by clicking here at the bottom. It says interaction distance. And if you just keep clicking, it goes from small, medium, a little larger, and full. And feel free to explore all the areas. On the right-hand side here, you can see a list of participants. Right now it's just me because the area is still password protected. And but you can then find somebody by clicking on that person's name, and it will give you an option to show you an arrow how to get to that person. What else is there? These are kind of, I think these are kind of the key points. And I guess we'll see all of you later in this space in about 25 minutes. Well, it's right now password protected, so we open it up as soon as this Q&A session is over. So here you can see the topic rooms. Here's a room on MATLAB. So if people are interested in MATLAB, they might just go there and meet. This is more of a conference room, and there's also some whiteboards. If you have a tablet or writing capabilities on your computer with a mouse, you can just stand in front of this whiteboard, and you press X. Then you can access the shared whiteboard, and you can actually then you can draw on it. So there's a few of these interactive tools around, and you can just walk around and explore them. Going back to the main area here. Some of the areas are blocked off. You can for example see that right now here there's a bunch of plants in front that don't let us through to get to the dock. Depending on how many people there are, we'll open these extra rooms to make sure there's a sufficient but not too high density of people in all of those rooms. All right, so that was a quick introduction to Gather. Just wanted to share it with you so you have a basic familiarity if you haven't used that before. All right. The last thing before I get to the questions is how to update EasySpin. Well, you can always check the website and download the latest version. But once you have a version installed, you can just from the command line in MATLAB check whether you need to update. And you just type EasySpin update and then press enter. And this will actually pull the EasySpin web server and ask if there is a more recent version. In my case, I'm using the most recent version, so there is no update available. So that's something that should work for you and should make it easy to update. So we've got a couple of questions. One that I found interesting and important to talk about is about different line broadening models. When to combine them, when you can combine them. So as you've seen, we have this sys.lwpp, which gives you some convolutional broadening, right? And then we have sys.hstrain, for example, or A-strain, or G-strain. And these are all strain broadenings. Let's write them out. G-strain is for the G-tensor. A-strain is for the hyperfine tensors. And H-strain, which stands basically for Hamiltonian. H stands for Hamiltonian. It means just the energy level. The energy levels are scattered. Whatever it's G or A tensor, doesn't matter. Just a very generic distribution of energy levels. And H strain and G and A strain and LWPP can produce very, very similar effects, right? So I discourage you from using them at the same time. You really have to think about, first question to answer when you do model broadening is A, do you want to think about the physics behind or not, right? And so if you don't want to care about that, and you're just really just interested in the line shape positions and you don't want to have perfect fits, then use the convolutional broadening. And that is often a very good starting point. Now, you might not be able to fit your spectrum really well with that because broadening always has a physical origin. In that case, you have to move on to the next level of line broadening modeling. And you have to basically choose which of these strains to use. Okay, so that will depend on your system, and I would suggest to consult the literature on that. The simplest way to go about is to first use H strain. Else, the LWPP is an isotropic broadening, right? So it applies in a powder spectrum, it applies to the same whether it's the X, the Y, or Z direction, and it's in millitesla. Whereas the H strain can be isotropic or anisotropic. And it's in megahertz. Let's quickly see how these two can produce the same effect. So first, let's define a spin system with a G-tensor, 2, 2.1, 2.2, and let's add some line broadening. Okay, that's a line broadening of 1 millitesla. Okay, then we specify microwave frequency, 9.5, and we'll simulate the spectrum. Okay, so actually let's specify the range manually. Now that we have the first simulation, it's probably from 300 to 350 is a good range. Run this again. Yep, that looks good. Okay, now we're gonna take the same system, run it again. We'll call it sys1, but we're not gonna use LWPP, we're gonna use H strain. But now we have to convert it to megahertz, and 1 millitesla is about 30 megahertz. And we're gonna now simulate both spectra. Now I have to run this twice and ask EasySpin to return the spectra. And finally plot both of them. Control Enter. Right, and you can see there's perfect overlap between blue and red. I can change the H strain a little bit larger to make it larger. As you can see there, they don't quite They don't, this one, sorry. They don't quite agree. There you go, okay? So I just made a small mismatch. They don't quite agree. Now, if this works for you, if this matches your experimental spectrum, you can use LWPP or H-strain, isotropic H-strain. Makes no difference. But as soon as you have an anisotropic situation, where different parts of the spectrum are broadened differently, like 35, 50, 100, then, like this here, look at the red spectrum. Low field is much more broadened than a high field edge. Then you do need to use H-strain. H-strain is basically the lowest level of modeling for an anisotropic broadening. It's generic, it's not convolutional, but it's generic, does not make specific assumptions about the broadening mechanisms. So I would say level 0 of modeling is LWPP. Then level 1 is H-strain, which allows you to go anisotropic. And then level 2 are the tensor strains. Right, you need G-strain, H-strain, and D-strain. Okay, and never mix broadenings from these different levels. That is kind of the bottom line of this line broadening. Okay, I think that was an important question. There was also any questions about isotopes. Okay, how much they slow down a simulation. For example, let's take a copper simulation, right? A copper simulation which has some G values of 2 and 2.2, very crudely. And the nuclei, let's take just copper. And let's take a hyperfine coupling of 20 and like 400. And simulate the spectrum. You probably have to drop the low frequency edge a little bit to accommodate the full spectrum. And we probably should add a little bit of line broadening as well. Start out with 1 millitesla. Okay, I think this is a little too low, the edge. All right, so here you see a typical copper spectrum. It has the Z direction, it has resolved hyperfine with 4 lines, because both copper nuclei are spin 3/2, so they have 4 hyperfine lines. You can see that there is structure to them, right? And the reason is that the outer one is from copper 65 and the inner one is from copper 63. So these are basically 4 quartets that are almost the same splitting, but not quite. And the reason for the difference is that they have different gyromagnetic ratios. So if they sit in the same position in a molecule, they just respond differently, or they couple differently to the electron spin. And how does EasySpin handle that? Well, first it looks up, what are the copper isotopes? It finds there are 2 of them, and then it runs 1 simulation for each of them. So in the case of this simulation, the simulation time goes up a factor of 2 because you have 2 isotopal logs. If you just specify copper 65, then simulation is twice as fast, and you only see just a 1 clean 4-point hyperfine splitting, right? If you have titanium, let's take the case of a titanium here. The hyperfine, the G and hyperfine values don't match, but for titanium things get a little more complicated. Because in addition, you can see there's now multiple things going on. We fire up isotopes, and you look at titanium, you can see there is titanium 47 with 7% abundance with a spin of 5/2, and titanium 49 with a spin of 7/2 with a 5% abundance. And all the remainder of the titanium isotopes are non-magnetic, so those lead to the sharp central line where the molecule only has the unpaired electron and nothing else magnetic that's relevant. And then the other peaks are from these other isotopes that are present in the magnetic isotopes of titanium. So I hope that answers that question. Okay, Bader Bruin asked about if relative intensities between a spin 1 and a spin 1/2 system are comparable. I think they are, because we're using the same theory for everything. So the transition matrix elements that calculate those intensities should make those spectra perfectly comparable. So at least theoretically they are. And I don't think anybody has reported to us an actual comparison of a triplet with a radical signal where they did spin quantitation. It would be great to hear about that and how well EasySpin represents the relative intensities. So what else? Yeah, somebody was asking about how to simulate lanthanides. I think it was Lei Sun. Where neither the spin nor the orbital angular momentum are well defined. And you can actually squeeze these types of simulations into an EasySpin jacket. And the way to do that is basically to use the S field for your total angular momentum quantum number like J, and then use very generic Hamiltonian terms. Instead of a G tensor or an A tensor, you can use higher order operators. And I'm going to show this here in the spin system section. If you scroll down, there is a section on orbital angular momentum and spin orbit interaction, but there's another one about higher order operators. So what you can do, you can specify so-called extended Stevens operators that allow you to build any Hamiltonian you want that still kind of fits in the angular momentum picture. Doesn't have to be spin or orbital, it can be just some generic angular momentum. These extended Stevens operators are quite some beasts. I'm clicking over here to the reference, and they're given here. But this way, you can build basically any Hamiltonian that is based on angular momentum. So answer is yes, you can simulate lanthanides with EasySpin. What other let's look for another question. One question was when to use which level of theory. We've seen that both for garlic and pepper, you can choose which theory level you want. And there's always the exact level that makes a minimal number of assumptions. And then there is some sort of approximative treatment that is much faster and takes less memory. So I would recommend always use the exact. And then go back to like a more approximate treatment only in special circumstances. And one of them, of course, is if you want to understand how your spectrum comes about. Often we think in a very first order perturbation theory picture, that the splitting is, hyperfine coupling and hyperfine splitting are the same and so on. And if you do a perturbation calculation, then you can see how that differs from the exact treatment, and that allows you to kind of learn a little bit more about the physics. So that's one reason you would go to a lower level of treatment. And the second is if your spin system is really large, it has an electron spin and maybe 5 or 10 nuclei, then the exact treatment gets very taxing on your computer. You need a lot of memory and a lot of time. But very often out of these 5 or 10 nuclei, only very few of them are strongly coupled. Only a few have large hyperfine couplings. So what you can do, you can keep the exact treatment for those nuclei, and then you can use perturbation treatment for the other more weakly coupled nuclei. And this is often a reasonable approximation. If you have this situation, of course, it's hard to test because you're going to reduce the theory level only if you need. The way to test it is to do a single crystal simulation, right? A powder simulation takes like 100 times longer than a single crystal simulation. Do a single crystal simulation with the exact level and with the perturbation level and see if they match or if they're close enough. And if they're close enough, you can then do a powder simulation at the perturbation level. So that's one way to go about it. A second strategy is to just drop 1 or 2 nuclei and to reduce the system size a bit and then see whether the exact method and the perturbation method are kind of consistent. And as long as you just add nuclei with small hyperfine couplings, you won't mess with that relationship between exact and approximate theory. And this way you can just be sure that you're not screwing it up. So that was another question. I'm going to go switch over to the Slido right now and see what are the most popular questions and briefly react that. Okay, and thank you, of course. There was a question whether these sessions will be available on YouTube, and the answer is yes, so you can rewatch. We know that some of this might be fast for some of you, especially if you're not familiar with that particular area of sub area of EPR. But we wanted to have something for everybody in this in this workshop, in this academy. But you can always come back and watch the streams later. Happy hour password. There is no happy hour password. It's password protected now, but we're going to open it in a few minutes, I think in 10 minutes. And then everybody can just join with the URL that's provided. I think we talked about the line width strain. We talked about this here. Sonia is asking about global fitting multiple spectra. I will talk about fitting tomorrow. I'm not entirely sure we're going to get to global fitting much, but what you can do with chili, you can also do with pepper. So there is no difference. So what else is there? While specifying the G-tensor in EasySpin simulation, is it always in the order G, X, Y, Z? Or do the order in reverse also work? If specify the hyperflow tensor also in the same order. So yeah, what about the order of the values? Maybe that's an important thing to talk about. The important thing is to always consider there is a molecular reference frame, right? And G is on A and all the tensors are defined relative to that. So if you say sys.g equals, let's say 2, 3, and 4, then the first one, these corresponds, these give the tensor x, y, and z directions. Okay. If you have no tilt between the tensor and the molecular reference frame, then the tensor x aligns with the molecular x from the molecular reference frame, which is also, we can call this like xm, ym, and zm for the molecular axes. And the tensor g's, let's call them xg, yg, and zg. Right. If you don't specify a tilt, the xg aligns with the xm, and the yg with the ym, and the zg with the zm. Right? If you specify a tilt, sys.g frame, right, you could specify now 0, pi over 2, 0, then that will turn the tensor based on these Euler angle prescription. And then you will, the angles or the axis will not align anymore. But if you don't specify this, all the tensors are initially aligned with the molecular reference frame, which is fixed to the molecule. And again, maybe go back to the documentation here and show that this is a very important page here about coordinate frames that defines how these frames are defined. Right? There's the molecular frame, and that's just a reference frame that's fixed in a molecular paramagnetic center. Right. And this molecular frame is of importance, for example, if you're doing quantum chemical calculations with ORCA. ORCA does the calculation within some sort of frame that derives maybe from the crystal structure, right? So that the XYZ axis from the crystal structure, they will make the molecular reference frame. And there's a function in EasySpin that allows you to import ORCA results directly into a spin system for EPR simulations, if you've calculated EPR properties. And this import function will use the ORCA kind of simulation frame as the molecular reference frame, and all the tensors are oriented relative to that. Okay, I hope that clears that up. There is some people upvoted questions about where they can download the folder and script files. That is on the EasySpin Academy website, easyspin.org/academy. One of these bullet points, you can find it here, yeah, is a zip file containing all demos and exercises. You can download it here. And at the end of the workshop, we'll provide a new zip file that contains all the solutions to the exercises. We've written them out already, but we're probably going to do them with some minor adjustments based on the experience from these workshops. So at the end of the workshop, you'll get a file with everything that will allow you to retrace what we did in the workshop. Let's see if there's any other questions. There is some questions, requesting specific topics. We're gonna do the specific topics on the third day, on Thursday. So those sessions, we still haven't planned them out. Depends a little bit on your feedback. And we are planning to hold a poll about which topics to cover tomorrow morning. So we'll be able to collect some input from you guys separately on what to cover. Okay, so watch out for a poll tomorrow, and please participate in the poll if you want your topic to get covered. I can't promise we'll be able to do it because there's only limited time and there's so many different things. EPR is such a rich field that it's been a challenge for EasySpin to keep everything organized together so that everybody can simulate their spectra from the lanthanides up to the organic radicals across the periodic table. Okay, let's see if there's anything else. There was one question by Hugo about how many nuclei one can maximally include in a spin system. In principle, there is no limit. It really depends on your computer resources. If you have, adding nucleus, if you add a proton, it will increase the spin system Hilbert space by a factor of 2. Right? And so if you add 10 protons, it will increase the spin space by a factor of 2 to the 10, so it was 1,000. So the memory requirements to setting up the matrices get larger and larger, right? So you need many gigabytes of memory for large spin systems. But EasySpin has no hardwired limits. You can have as many electrons and as many nuclei in your spin system as you want. Okay. What else is there? There's one question from Tanya that just came in. Maybe that's the last one we'll take here before we head over. The principal direction corresponds to the rotation of the molecular frame. Actually, let's go back and actually look at this example right away. So let's take a G-frame rotation of 30, 50, and 10, convert that to radians, and now fire up the new function rotview sys.gframe. We can actually feed it already a set of Euler angles, and we'll use those to construct the plot. So here is the plot. Okay, so what you can see here, you can select here that this relates to a G-frame, and if you click here, it will label the axis correspondingly. So you can see this, the molecular frame with the M here, XM, YM, ZM, in dashed lines. And then the tensor frame is labeled XG, YG, and ZG, and also indicated with this tensor ellipsoid or tensor potato. So basically what the Euler angles give is the rotation you have to do to take the molecular frame to align with the tensor frame. While the tensor is fixed in the molecule, we're not going to rotate the tensor. We're just going to look at the frames. So you take the molecular XYZ frame, and then figure out what Euler angles you need to rotate that molecular frame to match the tensor frame. That's what these angles mean. Okay, I think that is probably enough for today. And we're just 1 or 2 minutes away from the happy hour, so I won't hold you up. Please join us over at GatherTown and let's hang out. Make sure you be aware that your video will be on, but you only will be visible to people who are standing close to you. Okay? So thank you for participating on day 1. We'll start day 2 at the same time tomorrow, so 7:30 Seattle time, and I hope to see you all there for lots of talking about least squares fitting. See you in happy hour.